Good morning, everyone, and welcome to the East Coast Surficial Model ECSM peer review meeting. This is our fifth peer review meeting that we will be having today. My name is Alicia McGlaw with the South Florida Water Management District, and I will be facilitating today's meeting. Just a reminder, we have the same panelists serving on this ECSM peer review panel. Our panel chair is Dr. Wishingu, and we also have Dr. Michael Sukup serving on the panel as well. The slide shows our ECSM modeling team, which is the same as the previous meetings. So on today's agenda, we'll start off with opening remarks, which will be followed by a discussion of our input data sets. Next, we'll go over our model calibration results. And then we'll follow it with a Q&A from the panel and a discussion with them. But panelists, as in previous meetings, feel free to stop us anytime during the presentation to ask your questions or comment. Once we're done with the official panel discussion at the end of the presentation, we will open it up to the public for comment. And at that point in time, I'll go over how the public can unmute and mute their phones to provide their comments. So with that, we'll go ahead and get started with the opening remarks, and I will turn that over to Pete Wykowski and Anushi Obesekera.
Good morning. Thanks everyone for attending. Excuse me. So this has been a long process. I checked my notes, Kevin. I saw our kickoff meeting was February 2020. You might have started earlier than that on some of the stuff, but so it's been a long time in the making, and it's been a true team effort. We had our hydrogeologists doing the updated hydrostratigraphy, which resulted in the model layering. We had Kevin's group, the groundwater technical unit, doing all sorts of things on data analysis and pre and post processing and all that stuff. But there are three people that I feel are really need to be recognized today. And the first one is Jeff Giddings, who unfortunately passed away 2.5 years ago, and he was the lead modeler of our Lower East Coast Surficial regional model that was the predecessor of this one, and just a superb modeler, great guy, and we wouldn't be here today if it wasn't for all the work that he did. I greatly appreciate that. The next person I want to recognize is Kevin Ralberg. I don't know that there's no way we would be here today if not for Kevin. We decided when we had our kickoff meeting talking about what we wanted to do and recognized that we needed CWAT to do a density dependent model, but we also recognized that we needed to have the wetland package as one of the main features, just because of the footprint of the Everglades system and how central that is to everything that we're doing with the modeling. And there was no way to do that without rolling up your sleeves and taking CWAT and then incorporating the wetlands package into that code and a host of other packages as well. And there's no way we would be where we are today without Kevin's involvement in doing that. And it's just an incredible effort that he did to allow us to have a version of CWAT that incorporates the wetlands package that has all the functionality of wetland systems in the model, which we thought was so critical. And then the third is Anushi Obesekera. During this whole process, excuse me, she took over being the section leader. So in addition to actually being the lead modeler on this stuff, she was managing the unit. We had, we had some openings in the group, and she has now ably filled them. I mean, only recently did we have our full complement of groundwater modelers in the group. And so while juggling all the managerial and technical stuff dealing with ECSM, she's managing a group of groundwater modelers and recruiting and bringing in a great team. And once again, the third person, I think it's a team effort, but there were three people that really allowed us to be here where we are today. And Anushi is right at the top of the list of that. So I just wanted to recognize everyone that's been involved on the groundwater modeling team, our peer review panelists, esteemed, that are, have worked with us on and off for the last 3 years now to get us to, and incorporating their really good guidance and input and allowed us to be in the position that we are today. And so I'm really excited. Anushi teases me about using this term, but this is our flagship groundwater model for the district. There are about 7 million people that are in the footprint of our model here, and we're doing water supply planning for 7 million people. And over the next 20 or 50 years, we're using this tool to project out as the influence of population growth, water supply demands, potentially sea level rise and climate change, all of those things. And now, after spending over 5.5 or more years working this, all of this effort, we're finally in a position now to present to you the results of the calibration of this tool that we hope to be using in short order to do the thing that we wanted to do when we envisioned back then, which was we needed a density dependent groundwater model to really evaluate the effects of increases in water demands and sea level rise and climate change on our water supply system, and hopefully be in a position to identify the vulnerable areas and then allow water managers and others to do something in advance of whatever could be coming in the future. So with that, I'd like to turn it over to Anushi to take over the rest of the meeting.
Thank you. So, you mentioned my name is Anushi Karen. I'm going to be discussing the objectives of ECSM. So when we started, we kind of wanted to refamiliarize both of you with why are we here in like overall, what was the goal of ECSM? And so it's critical to remember ECSM is a density dependent model. We wanted to span the East Coast planning regions of our district. And so what we're going to be doing with ECSM once we say it's calibrated, which what we're saying today, is that we're going to use the model to evaluate water supply demands over a 20-year to 50-year planning horizon, right? The way we're going to do that is we're going to take the model, we're going to run some scenarios, and we're going to look at the differences and look at the delta in those scenario runs. And that's how we're going to determine if there's no undue effects on existing legal users of water and natural systems. So it's a water supply planning tool. We're going to simulate and evaluate the effects of sea level rise and saltwater intrusion on the groundwater system using ECSM. And just a basic overview of ECSM, again, it's a 5-layer groundwater model, density dependent. We have 1,000 foot by 1,000 foot cells. Our calibration period is 1985 to 2012. Our verification period is 2013 to 2016. So we just run everything all at once from 1985 through 2016. We are calibrated to water levels on a daily basis. Water quality, which is in total dissolved solids in milligram per liter, is on a monthly basis. And our structure flows are also monthly. And then looking at the actual hydrogeology of the system for the 5 layers, we have layers 1, 2, 3, 4, 5 here on the diagram on the left-hand side. You can see the stratigraphy, the lithology of the hydrostrat for the model, with layer 2 and 3 being the productive zones of the Biscayne aquifer. And with that, I'm going to hand it over to Jose to start talking about our input data set.
Hello, my name is Jose Grisales. I'll be talking about the I-bounds, the IC bounds, and then the constant S factors. So for the I-bounds are at least 3,000 cells offshore, or 3 cells offshore, 3,000 feet. And we did that in an effort to move the boundary conditions further east to a place where we felt we were comfortable with. And then the locations for the initial boundaries are in the same place here. Okay, this is not working. So right around the west edge and the north edge, and then this is showing the general location of those I-bounds for layers 1 through 5, which are all identical.
Excuse me, and I'm sure Wei-Jing already knows very well, but I've worked with these before. Could you remind us what they do?
Yeah, so the initial boundary conditions set the cells as no flow cells and keep that same initial water level head repeating at those locations.
Okay, so it's just like setting the constant head boundaries there.
Well, there's a slight difference between the constant heads and the I-bounds because the constant heads that we use, which I'll talk about in a little bit,
Right.
Vary that water level head by stress period, where these repeat the first initial water level head throughout the whole model.
So essentially our I-bound file will either say 1 for an active cell, it'll say 0 for an inactive cell,
That's okay.
and then we'll have a -1 if we're setting a boundary condition, which is what we have for our CHDs.
Okay, I got you. Okay, yeah, I remember. now. And then there's another one. Perhaps you could explain too.
The IC bounds?
Yeah.
Okay, yeah, so that's what we're getting into now.
Okay.
So these are the initial concentration boundaries, and so these regard the transport model side of things. And so they also, similar to what Nushi was saying, the active cells are 1, inactive cells are 0s, boundary conditions are -1. And basically they let us set that concentration as a constant concentration. That's what's called IC bounds. And the locations of those at layer 1 and 2 are in the same exact locations as the I bounds. There's a slight difference coming. So for layer 3, the IC bounds shift 1 cell to the west. And then for layers 4 and 5 are identical, but they shift another cell to the west. And so the thought behind that, what we're trying to do is mimic the salt waterfront, where as we get closer to land, the saltwater wedge is deeper, right? So the deeper we go, the closer to land the saltwater wedge gets. It's kind of.
So, excuse me, I have a question. So the IC bound is along the coastline or along the west, east boundary?
It's so for, like I said, for layer 1, it's at least 3,000 feet from the shore. Because it's at the same location as the I bounds, right?
So is it in the water or in land?
It's in the water.
It's in the water.
In the water.
Yeah, it's this green line here. It's right off of those
It's off of the barrier islands.
Okay, so after 2,000 two cells shift, that will be 2,000 feet in water, right?
Yes.
Yeah, at least 3,000 feet in water.
Will be that in land, that's in aquifer, right? So.
Yes,
Yeah, I'm sorry, that's a good question. All right, okay.
All right, and then so yeah, so as I mentioned, like 3, 4, and 5 are kind of mimicking that wedge. All right, so now we'll talk about the constant heads. So these are time varying constant heads. So the concept there is that during one stress period, that constant head or that water level head value is going to be constant throughout that one stress period, but we can vary it by stress period. Doesn't mean it does vary every stress period, but it can, and it is provided daily values. And how those stages get set is based on best available data, which I'll go over in a little bit. But first, I want to go over the locations. So for layer 1, the CHDs are located at the exact same locations as the I bounds, which also makes it as the same locations as layer 1 and 2 with the IC bounds. And then in layers 2 through 5, basically they're located at the same location at the north part of the model and the west part of the model. And then on the east edge there, we don't use CHDs at all. They're just normal active cells for layers 2 through 5. And so these maps show up for layer 1, and then these ones show up for 2 and 5. Here you see them in green, over there you see them in orange. All right, and then as I was mentioning, the stage data for this information is based on these stations here. So right here, we're just showing the general location. On the left-hand side maps, you'll see the stations that got used to assign those water level heads for the west and north boundary of the model. And then on the right-hand side map, you'll see the tidal stations that got used to assign the east time varying constant heads. All right, now I'll turn it back to Anushi to discuss initial conditions.
So the last time that we met, with a little bit over a year ago, I think, we were presenting our historical data points that we were using to develop our initial conditions. And one of the thoughts that we received from the panelists was, how are we developing those initial conditions? What should we be doing? So we took your advice. Basically, we started with all the historical data, the observed data points. We interpolated them. For the water levels, we used a Kriging interpolation method. For the water quality, we used spline. And then we created that 1985 average scenario, and we ran that through our warm-up simulations. We did that, it feels like more than thousands of years, until we reached that equilibrium. And then we went back and then we said, okay, here's our array. That's our endpoint from those warm-up simulations. But we wanted to make sure we didn't deviate significantly from the historical data, right? If we did, we went back to what was historically observed in 85, and we developed our final initial conditions that way. So it's very similar to wishing, I think that was your comment. That's kind of the methodology that we use to develop the condition. So basically, here's what we ended up with. The left-hand side shows our original creaking. We took our observed data points, we creaked it. Here's what we initially started with. We ran through the warm-up simulations, and we ended up with the map on the right-hand side, which became our final set of initial conditions that's fed into our final model runs for the calibration. Then looking at all the layers 1 through 5, you can see the map of all of the initial conditions that we've developed for the water levels. And then again, same process for the water quality. We started with the line version of the historical data. We ran through the warm-up simulations. Now, for the water quality, we did have to go back and change to historical data because what we found is that there's some connate water underneath in, I think it was layers 2 or 3, and it just spread out drastically over those warm-up simulations. So we definitely had to go back and say, that's not historically what was observed. We need to go back to historical data, right? So that's why you'll see this is kind of in layers 3, 4, and 5. You can see a little bit of that connate water. It just spread out all over the place. And we knew that's not historically what we saw in 1985. So we had to kind of do some editing for layers 1 and 2. But this is actually the final data that we used as our initial water quality arrays feeding into the model. And then we have our tidal data. So Jose mentioned the constant heads, and he talked about on the left-hand, or not the left-hand side, on the west side and the north side, we use some surface water data. On the east side, we use tidal stations. So here you can see, and this was actually presented at our kickoff meeting, but I just wanted to refresh everybody's memory. On the right-hand side, you can see all the tidal stations that we used. They are a combination of NOAA's harmonic and subordinate stations. Basically, what we do is from the harmonic data, we can get the historical sea level rise trend that's occurred historically from 85 to 2016, right? And then we place that trend on all of our data because the data set we originally had was detrended. So we set sea level rise at 0 for 1992, and then we implemented that trend line to get our tidal data that's fed into the constant heads. So with that NOAA data set, we had daily tidal data. So that meant that we could use our constant heads with that daily step. So every day our tide changes in the model. And it's the same thing for the north side and the west side, where we're able to use, we call it a time varying constant head. Because I know sometimes constant head makes you think, oh, you're just using one value for the entire 32 years. That's not what we're doing, it is time varying.
Excuse me, so that particular graph is like monthly averages or something?
So this particular graph is just showing Virginia Key. It's actually the variation in the tide. So you'll see that it's varying. You'll have your lows and your highs over, your month, but we're maintaining that high and low trend, but we're basically putting in an increase that's seen over historical time. So that's kind of how we did it. And then for aquifer parameters, rivers, and drain coverages, Jurgen.
Good morning, and my name is Jurgen Masagid. So I'll be presenting on aquifer parameters, rivers, and drains. So first I'll start with the horizontal hydraulic conductivity. So this was derived from aquifer parametric tests and other methods from the field data. So that was created and applied to the model as an array. So what happens is after applying into the model, we just did some global as well as localized level sensitivity analysis and try to change a little bit of the data, but still honoring the observed data from APT. So that's what was the process of As you can see, layer 3 and 2 are the most productive zones because here it shows this blue is more than 50,000 feet per day, which is representing the Biscayne cable. And the other layers are relatively tight. The vertical hydraulic conductivity, we used 10:1 ratio or a tenth of the horizontal hydraulic the conductivity, which is a rule of thumb. But we just did also some localized level changes during our calibration process. The other aquifer parameter is the specific yield and storage coefficient. So we reviewed literature and other modeling exercises, which happen to be in Miami-Dade, Broward, especially around the Biscayne aquifer. So for layer 1, the specific yield, what we found was 0.1 to 0.9. So the model value we landed in was 0.2. For layer 2 to layer 5, we applied uniform. We did some sensitivity analysis again, and the value we used was 0.001. But studies show it varies from 10 raised to -5 to 0.03. In some circumstances, 0.15. But we landed at 0.001. Yes.
So from layer 2 and 5, that's the storage coefficient or the specific storage? What's the unit of that? 0.001.
We're using the storage coefficient.
Storage coefficient.
Yes.
So that means the thickness has been considered.
Thickness has not been
Yes.
considered yet, yeah.
Thanks.
The river package, this is one of our inputs. And we use the district canal network, estuaries and transcoastal waterways. And because it's heavily managed, and particularly we use the primary and secondary canals for the river package. We calculated the river conductance according to the literature. Still, we just did some testing and tweaking on the values of the river conductance. That probably when I presented on the ET recharge, I'll just briefly discuss about it. So the values of river conductance range from 1,500 in Everglades agricultural area up to 1,000,000 feet square per day in South Miami-Dade area. The river bottom elevation we use is based on the best available information, primarily the upstream and downstream structural bed elevation. So wherever we found structures, we just check the survey data or upstream bed elevation and the downstream bed elevation. So we just applied it. This was as much as we can. Yes, go ahead.
Yeah, for the second one, you said model calibrate the river conduct for Everglades agricultural area to 1,000,000 square feet per day. Is that calibrated value or is it standard value to it?
It is calibrated. Actually, in some circumstances, it is higher than that one, especially in the South Miami-Dade area. Deep South, it is higher than that, but that was the calibrated value.
So the Everglades agricultural area is the 1,500 feet square per day. In South Miami-Dade, that's where we have the 1,000,000 feet square per day.
I mean, that basically nothing there, right? So that means the full open.
Yeah, basically.
There.
Yeah, so that's why I wanted you to give a high value or whatever it is, right? So, okay, yes, thanks.
So the drain package, we use typically smaller canal networks in agricultural areas and mostly up in the north, as you can see right here. So the drain conductance is calculated just like the river conductance using the well-established methods. However, the drain bottom elevation, we just have to collect data from different sources. One of the sources was the environmental resource permits, wherever it is available. We use some district canal management because they do so much operations, especially removing sediment and everything. And from them, we just get some bed elevations. And where information is not available, we use the topo minus 5 feet. So
Where do you get the 5 feet?
I'm sorry.
How do you use the 5 feet?
So that was actually one of the things that we, in previous modeling, calibrated our model with. The 5 feet was something that we had determined, for the northern extent of the model. What we found is that we tried, that portion is covered by another model, ECFTX. And so in that process, we had tried 2 feet, 3 feet, and 5 feet to see what is better calibrated for all the structures in that area. And so 5 feet was what we had stuck with. So we said, okay, since if we calibrated that model with that, let's use that for ECSM as well.
And you apply the number for the whole model?
In ECFTX, yes.
It was when we didn't have other data.
If we have, so basically what happens is when you're looking at the drain coverage, you'll notice that we have places like, in there. Let me see. So, hard to navigate, but down here, this is Indian Trail, Water Control District. They have set assumptions for, this is how we operate in the wet season, this is how we operate in the dry season. So that's an example of the second bullet, Water Control District Canal Management. If we have that information, that's what we're using. Then, if you look right north of in the Martin County area, that's, it's a big agricultural area with Hope St. Lucie Conserve 2 or something like that it's called. They have an ERP permit that says, okay, this set of agricultural canals are controlled this way. It feeds into this ditch, which is controlled that. And so all of that information was used for our drain controls, but you can see how many drain cells we have. There's so many other areas that we don't have any information for. So we just kind of had to figure out something. And that's when we said, okay, the 5 feet had worked in that northern area. Let's use that to represent this too.
So for the drain, basically just remove water from.
It's just
aquifer,
remove the
right?
water.
So
It's
for
from
the
the
river pipe, you can do the both either way.
Yes.
So what's it, why you chose to not use the river?
So we don't have stage information for this area. So what we had to kind of figure out is, okay, we know these are small ditches that are mostly agricultural areas. You know, the little canal networks that they have for citrus groves and things like that. We wanted to model it. We don't have daily information, so we can't really use the river package. We said, okay, let's try with the drains. That's what we've been successful with so far. We don't really care about how much water is moving anywhere. It's not a heavily managed canal system. So we said, okay, this is, you know, a better way of conceptualizing it without knowing enough to do it. That's why on the other side, when we go to the EAA, it's all rivers because we have more knowledge about how are the areas controlled in this situation. So it just kind of depends on the area that we're looking at and how it's conceptualized. So for example, here, Lake Worth Drainage District is all rivers. But on the other side, ITID is drains. So there was a lot of like decision making that we had to do, thinking about, okay, what does this area represent? What do we care about? Where does this water go? How do we need to decide what to do?
So will the model consider how much water you remove from the ditches, add them to the surface water?
So that we have in the southern extent of the model,
Not in the north.
not in the north.
So they remove it by drainage,
It's
removed
just-
from the model.
yeah.
Okay.
Yeah, that's the whole purpose of the drains. So just to remove if the groundwater heats up to the vegetation.
Yeah, I understand. I just wonder if you count that part from water to the whole water budget.
I'll discuss.
Yeah, so when we think about a water budget, we actually have this, what is multi-bud considered a code or is it
Yeah.
Yeah. So multi-bud will tell us on a daily basis, how much water is being removed from the drains. So we can see how much would go. The only thing we're not doing is routing that water somewhere else, but we can see how much is being removed.
All right. So the other package that we use as an input to the groundwater flow model is the evapotranspiration and recharge. So the ET recharge program uses AFSRS. It's called AFSRS is an abbreviation for agricultural field scale irrigation requirement simulation. And probably this is just a recap from what you presented before. So the program uses reference ET, land use, soils data, crop and irrigation data as inputs. And the driving force is rainfall plus return flow. The return flow is the irrigation. So it's just a little different. So initially, we applied the curve number method on the rainfall and return flow, and we separate the runoff from the rainfall. So once runoff is separated, we use the effective rainfall and applied on AFSRS. So this is a Fortran program developed by University of Florida, and the program generates potential gross recharge and potential groundwater evapotranspiration. So these two are inputs to the CWAT model. So both the potential groundwater evapotranspiration as well as the potential groundwater recharge, they are applied to CWAT, and CWAT generates actually canal decants, and I'll just discuss from sometime how we are using runoff and the canal decants to compare it with the measured structural flows at watershed scale and try to twin or tweak the river conductance and rerun the model again. So we use these two inputs just to add them up and compare against the structural flows. So that helps for tweaking the river conductance. Yes.
Just wondering, in the CWA, we use the MAFlow, standard MAFlow EP package, use the maximum that decrease with the depth, right? So that's, so what's the depth information you using in your model?
We have extinction depths depending on the land use type. So it varies from 0.1 up to 8 feet, and in certain areas up to 16 feet. So it varies from place to place.
Okay.
Yes.
So you have measured data, or it's just like an estimate? I know Jeff Gidding did a lot of work on this old model.
Yes, it's dependent on the land use.
On the land use.
Yes.
And it's based on all the work that he's done on the extinction depths.
Okay, yeah, I remember he spent a lot of time working on that.
Yes. Thanks.
Go back.
So.
Can you go back one more? No. Did you cover the runoff
Yes.
runoff canal leakage for the structure flows?
Yes. So that's, I mean, these two parameters are summed up together and compared against the structural flows. Once that comparison works, then we use to tweak the canal decants, we have to change the river conductance until we get major structural flows at watershed scale is the same as summation of the runoff and the decants.
So the canal in that box, it means the drain or the river, or the both?
It's a river, usually we use rivers because
In the river.
yeah, structural flows are measured on the rivers.
It's mostly rivers, and the
Yes.
budget comes from summarized, multiplied output, basically. It did summarize the cell river leakage from each one of the basins.
So the drains, you talk about in the north part.
No.
Yeah.
Because the drains just they remove the water from the system. So once it hits the drain irrigation.
Do they contribute to the structure flow?
So the basins that we're calibrating, no, they don't.
They don't.
So the basins that we're calibrating are pretty much in the southern extent of the model domain.
Yeah.
Those are our gauged managed structures, right? When you get north of basically like the C51 line, we really don't have a lot of managed canal networks like
Right.
that. In order for us to calibrate a structure flow in that area, we would have to do what you suggested with routing that water step by step through the structures into the canal network. And so right now we were at I think a model runtime of like 20 hours. If we were to put all those operations in, we would look at an extensive runtime with using, we have packages that do that. And we kind of said, again, priorities, we said it's more important for us to capture the water moving from Lake Okeechobee through the conservation areas into the urban, like lower East Coast area, not so much the upper East Coast area. So that's how we did it.
I got you. Yeah, unfortunately, I never traveled to that part to see how they
Yeah.
operate that canal there. That's a kind of a question you leave it out.
Yeah.
So, all right.
Good morning. My name is Brian Moore, and I'll speak briefly about the land use data. So we started with the South Florida Water Management District's historic land use land cover data, and we supplemented that with data from St. John's Water Management District along the northern boundary of the public extent. From that, we generated composite data sets that would then apply to all of the model years. On the right, and it's an example of one of the composite data sets. This one is the land use composite data for 2014. The graphic on the left details which composite data sets were used for which model years. For example, the 1988 land use composite data was used for model years 1985 through 1993. 1995 land use composite data set was used for the model years 1994 through 1997, and so on and so forth. And I'll pass you back to your. No, so it's not a solution.
Thank you. Okay, so Jurgelum had discussed kind of all the input files to the ET recharge program. And Brian discussed the land use. So two of the other big inputs are the climate data, our rainfall set and our reference ET. So for the rainfall set, we are using the district's rainfall data set. One of the key things with that is we thought about our objectives. And as we apply the model, we're going to be also relying on that district data set. So we want it to be consistent, right? So our district's rainfall data set is actually, it's a transient data set. We have daily data for the entire calibration period of record from 85 through 2016. Here on the right-hand side, you can actually see an example of 1994, which is a wet year. So all the maps here on out for ET recharge will be showing 1994. But we have rainfall on a daily basis for 1985 through 2016. That data itself was derived from gauge data from 1985 through April 2002. So they took gauge data, they then interpolated it using the TIN10 method, and that's kind of why you see the graphic looking the way it does. In May 2002, we started using NextRad data, and that NextRad data continues through December 2016. And we use average values to get then the gridded data that we have. That gridded data set is for a 2 mile by 2 mile grid size. So we had to use the nearest neighbor approach to get it to our ECSM grid size of 1,000 feet by 1,000 feet. And then one of the things that we saw once we did all of that is the southern portion, south of Key Largo, we didn't have coverage from our district data set. So we used rain gauge data, and that was interpolated to cover the extent with Thiessen polygons and inverse distance weighting. So that's kind of how we created our rainfall data set. Very similar approach for the reference ET. We have a district reference ET data set. It is based on a reference crop of green grass with 0.12 meters of height, actively growing, well watered, completely shading the ground, fixed surface resistance of 70 seconds per meter, and an albedo of 0.23. So that's kind of the standard for the district's reference ET. It's based on 2 meteorological data sets, NAR and Hydro 51. And when it was created, they utilized multi-quad interpolation. So that reference ET is computed using Penman-Monty. And then again, same thing. It's created for that 2 mile by 2 mile grid. It was originally developed for the water management model. So we just use nearest neighbor to proceed from their model to the 1,000 foot by 1,000 foot. And so once we feed in all the input data, what we're left with is the output from the ET recharge program. Here on the left, you can see the runoff in 1994. Again, what's important to realize is that in saturated areas, lakes and wetlands, runoff is 0, right? We're assuming that all the rain becomes recharge. Then in urban areas, as expected, you're seeing more of the red coloring because you have more runoff with more impervious areas. In the middle, we have the maximum evapotranspiration. So what's important to remember is this is just the maximum potential groundwater ET. It's not what's actually eating off. That's coming from the seawall side of things. But this is what's fed into seawall. And then same thing for the right-hand side, that's the gross recharge in 1994. That potential recharge that we could see what actually handles what's happening in the groundwater side of things. And then another big input that we have, the well package. So looking at the well package, we basically looked at all the pumping wells from the Surficial aquifer system. There are several different water use categories. The biggest one for this area from the Surficial aquifer system is public supply, using 82% of the water. The next biggest one, which is kind of surprising, is domestic self-supply, which is at 8% of water use. Then we have landscape and recreation at 5%, commercial, industrial, and institutional at 3%, and ag at 2%. Now that's kind of surprising because you think, oh, you've got so much ag and like the EAA and stuff, but that's all surface water use. Because we're focusing on the Surficial, we do not include the ag demands from the surface water system. So that's why the ag percentage is low. For public supply wells, basically what we did was we used our regulatory database and we queried well information, so the locations, the case depth, total depth, when the well was drilled, and we brought that into what would basically become our well package. Based on that regulatory database, from 1985 to 2007, all we had was pumpage on a permit by permit basis. We had to figure out how we were going to distribute that demand. So what we did was we said, okay, what wells were drilled in this time frame, and we evenly distributed that pumpage. Now from 2008 through 2016, we actually had well by well data, and then that is what we used. So there's definitely a noticeable difference in the well package when you're looking at it. From the January 1985 through December 2007, you'll see that it's evenly distributed amongst however many wells that permit actually has. But once you get into January 2008, you'll see that some wells are off, some wells are on. It's literally however the utility operated their well field. But the issue with that is our well package is very accurate, we feel, based on that 2008 to 2016 data, but it's not that great prior to 2008. So that was a little bit of a concern, but we said we had to honor, whatever we have, and this is the best available information. On the right-hand side, you can see the location of all the wells these are just the public supply again. And then you can also see here in the table, the average annual demand over the 32-year period of record by county for public supply. The most notable thing here is that the lower East Coast counties they dwarf the other counties when you're looking at it, with Miami-Dade at the highest, 364.2 million gallons a day. That's all of Miami-Dade's utilities, not just, WASD itself. So it's kind of where we are for the public supply. Now for the non-public supply piece, here on the left-hand side, these are what I call the irrigation wells. They're agriculture, golf courses, and landscape. This demand is completely estimated, and we estimate it using the ET Recharge program that Jorgelum discussed. So essentially, when that ET Recharge module was created, and using AFSRS, it has a NIR, the net irrigation requirement, and an ET deficit. That gives us a daily demand that's required for each of these, by cell, it gives us that. And then we aggregate which cells are associated with which permit, and then we distribute that demand. Now, the one thing that we do is that for each permit, we look at the allocation. If the NIR exceeds the allocation, we cut it back. We don't want to pump more water than they're permitted to pump. So that's kind of the only thing there for the irrigation wells. Domestic self-supply. Remember, that was the second biggest use class. And the reason it's like that is because you can see how many wells we have across the model domain. So those locations actually came from, the district has delegated agency contracts with different either departments of health or different counties. And they kind of keep track of all the well construction that's occurred in each area that they're responsible for. So when we started ECSM, we reached out to each of those delegated agents and we said, please get us a list of all the well construction. So that's kind of how we created this coverage. And then the last one is commercial, industrial, institutional, and there's one aquaculture well in southern Miami-Dade. So that's kind of how we created our well package. And then the next thing is the diversions and reinjection packages. So these are two district packages that were unique to a district version of ModFlow that Kevin had to kind of bring into CWAT for us. And the reason that they were critical is because they're the ones that we rely on for routing. So wishing you had asked, well, what do you do with the water that the drain removes, for example? This is kind of what we use. So here in the diagram is an example of diversions, right? The way the diversion package works is it looks at the source cells and the sink cells. And I can only move water, or the model can only move water, if the source cell has a stage higher than the rule that I set, and the sink cell has a stage lower than the rule that I set. So basically, I have enough water to move something. Okay, it meets that requirement. Now I can route whatever quantity of water I actually put in the input into the sink cell. So it's basically like a bucket method. Oh, I have enough water here. Let me pick it into a bucket and dump it into the cell that I'm telling it to go to. So that's the diversion package. It uses source and sink cells to move water from one location to another. I am setting the head upstream and downstream. So there's a operational rule file that we use. And then the flow rate varies on a daily basis. So this is good for things where I have historical data in terms of flow. Lake Okeechobee, for example. I know how much flow is leaving the lake. So that's the kind of situation where we would use diversion package. Reinjection drain flow is basically, if you're familiar with the DRT package, it's essentially the same thing. It takes what would be normally a drain cell, and once you reach that drain control elevation, it takes that quantity of water and it reinjects it to the sink cell. So with that one, I can actually change the stage on a daily basis. So we prefer to use the RDF package when we have stages changing on a day-to-day basis, or maybe seasonally. A lot of times I have operations where in the wet season, they're controlling the stage at this level. In the dry season, we're controlling the stage at this level. That's a good reason to use the RDF as opposed to the diversion, which just uses a set stage. So currently, the diversion package, one of the actual benefits of it is we can also bring in external runoff. What that means is Jurgelim discussed the ET recharge and how immediately when we have rainfall, we use the curve number method and calculate runoff. If we're trying to route that runoff into the areas or the canals that it's going to, we can use the diversion package. We say that it's an external source, but the sink is going into whatever cells in the model I put it into. So we're able to do that, and we have done that in certain areas within ECSM. That way we're accounting for the movement of that runoff in the canal network. It's also used to simulate water, like I mentioned, Lake Okeechobee, from one area to another. The RDF package is currently used in areas like STAs, the stormwater treatment areas, the conservation areas, and Everglades National Park. So that's kind of how the district routing packages work. So looking specifically at the diversion package, the left-hand side shows all the diversion source points. Now remember, source points are only the ones that are internal to the model. Any external runoff that I'm bringing in is not going to be mapped out here because it's external. It's basically assumed to come, I don't want to say from thin air, but basically there's not a cell that I'm assigning for that source cell. So this is the sources that we have. Lake Okeechobee, we have some runoff in the northern areas, and then we have conservation areas. And then the sink cells are shown here in the fuchsia color. So it's very hard when you're just looking at a map like this to know where's water going from one place to another. So what I did was I wanted to kind of show an example of it. So here's an example for S5A. So the structure S5A is used to move water from Lake Okeechobee into the conservation areas. So that's why here you can see on the right-hand side, in red, you have the source cells. So I'm pulling water from all of these cells, and I'm routing it to this pink area, right? And the way that I'm routing it is using these operational rules. Now, sometimes we have operational rules and we know that regardless, we're always gonna send water. So that's why you're gonna see kind of some funny numbers like 5s or -999s. That's to make sure it always happens, right? So basically what we're saying is anytime Lake Okeechobee is greater than 5 feet, you're going to send water into the conservation area as long as the conservation area stage is greater than -999, which it should always be, except if it's a dry cell, or if the stage is less than 16.2. So there's a stage constraint there. And then when you think about how much water are you sending, there is a daily flow file that says each day this is the flow that we would want to send if these rules are met. That's how it works. Yes.
So when you move the water from a lake to the STA, it's just like a instantaneously down, or is you count how many days actually
No,
water could flow?
Every day. It's every day. So instantaneous in that day, it happens. So it doesn't account for the fact that this water in reality has to go through a canal network.
Right.
That part is not accounted for.
It just move them.
We just move it like a bucket. Yes.
It's the limitations of a groundwater model.
I see.
Yeah.
I just wondered how much water you can fit into, compared to the size of the lake, because compared to the size of the SDA.
Well, the flow rate is basically governing the pumping at, I guess, 5A, the tip of the purple area there, right, is governing, there's a flow rate.
Yeah.
Okay.
That's like the main pump, right, and it's gonna distribute the water to the purple cells. It's gonna take the water from all of the cells like Okeechobee and evenly distribute at that rate over the little purple area.
I see, yeah.
Yeah, so because we have historical data for S5A, that tells us, okay, this is the water that moved into the system on that day. So we know that it's not like the benefit is it's not an unlimited quantity of water, right? We know how much water moved into the system. We use that to kind of dictate how much can go from Lake O to the conservation area. But it is like an instantaneous, we're not capturing the actual movement of water through the network.
Yeah, well, I was considering because the water is from the pump station going to the canal, that will, actually leak the water into the aquifer along the canal.
It's also, the purple area is also a wetland area, which is gonna have higher conductance.
Okay,
So it's gonna move pretty quick,
all right.
basically open water.
So then when you're looking at the RDF package, again, that's where it's essentially like a drain, but you're re-injecting the water. Here you have all the source cells for the RDF, and here you have all the sink cells for the RDF. So that's, again, hard to tell from this map where the water is actually going. So we picked an example that we wanted to share. So looking at water conservation area 1, right? Here, the green are the source points, and then the blue are the sink points. And then what are the rules that we can kind of move water with? So in the RDF package, basically we say the source cell stage has to be greater than, it depends, it's a daily varying stage, but 17 to 18 feet is kind of the rule that we have in there. But every day I have a new stage. And again, that's all based on historical information. And the sink cell stage is 99, which means it's always going to put the water in the sink cell. And I think that F99 term is what it's actually called in the package. That's, the stage is always 99 feet for our RDS. So that means our RDF, whenever the source cell stage is met, it's always moving that water. And then there's no flow associated, like a flow term associated with the RDS, but there's the conductance term. So that would be the knob to kind of dial whether you're moving too much water or too little water. So it's kind of an interesting way of us routing the water from one area to the next. The only difficulty that we had is historical data back to 85 is kind of hard to come by, right? So sometimes we had to kind of make assumptions for how were these things operated in that early period. And that, you know, lends itself when you're looking at kind of all the areas it's covered, it makes it hard to quote unquote calibrate a model when you're estimating how much water or when is it moving, right? So that was something that we really had to contend with. And with that, I'm going to hand it over to Kevin to talk about the wetlands and reservoir packages.
This map here showing the general extent of those the wetland coverage based on land use. You can see that the wetlands is pretty extensive throughout the area, so kind of emphasizes the importance of adding the wetland package in there. One of the challenges, though, is the wetland package is primarily to support regional wetlands. They're non-isolated wetlands. So Jose was did some analysis of the actual cell by cell wetland assignments, and we needed to remove anything that was less than 3 contiguous cells. So one of the challenges here is like you asked that those would look like they're all connected, those 3 there, but with the diagonal flow doesn't happen in mod flow. So those basically aren't what we consider. We consider those isolated. So those would be removed. So that's kind of a challenging task. Without doing it manually, he was able to get a pretty cool script. One of the other challenges was how to manage Lake Okeechobee. We tried different things in the past, but since it is a well-managed lake, it was decided to use the reservoir package. And yeah, we also have 4 little lakes along the east coast here in Palm Beach County. We also had really good data for. And one of the other challenges, you have to identify the reservoir bottoms. What is the bottom elevation? We have symmetry data, which is very complete for Lake Okeechobee. The 4 lakes here on the east, Lake Mangonia, Clear Lake, Lake Osborne, Lake Ida, are managed lakes, but we have reservoir bottoms. It's harder to identify. So we use like fishing data. Local anglers know how deep the water is in the areas. We are able to identify cell by cell information for that. We're also use the vertical conductance as a starting point for the reservoir conductance. We also modified by 10. I later found out it's like there's a 1 foot assumption for riverbed thickness, which could be reset. We set it to 0.1, I wouldn't have to multiply the vertical conductance by 10 in order to get an appropriate reservoir leakage value. Yes.
So the KV is the aquifer vertical conductance.
Yeah,
I guess he mentioned that's or the 10-to-1 ratio.
it is pretty much. So yeah,
that's
we better use horizontal. Yeah, yeah.
Is that reasonable?
But or I could have probably set the reservoir bed thickness to 0.1, which would basically divided the K, or which would have multiplied the K. You divide by 0.1 would be the same thing as multiplying by 10. So it's speaking about right.
Yeah. Also, can you go back one slide?
Yes.
I'm sorry, another one. Yeah.
Yep.
Yeah. So for second paragraph, you mentioned the 90-degree counterpart. I I didn't get a chance to understand what
Oh,
that,
see, this particular thing right here,
okay,
these would be considered a joint or contiguous, so water flows flow,
alright.
obviously it goes
Okay.
only at each
That's
face
what you
front
call
face.
90-degree.
Right, so there's 45 here, water flow doesn't route flow diagonally.
But Buffalo also can go there.
It could, yeah, definitely, so it can go this way and this way without any trouble. And with the wetland package, you can't go out here and then down.
I see. Okay, I got you. Thanks.
Sure. And, oh, and then we have daily stages. One of the things I was talking about, we had the well-managed lakes and things, we know what the stages are, and stuff in a daily basis. So stages identified, these are just hydrographs showing the different water levels that provided them that from our database and stuff. And transport of
Thank you.
Alright, back again. So I'll be presenting on transport input data sets. For the one, so the first one would be the dispersivity value. So we took longitudinal dispersivity and did some sensitivity analysis by putting values ranging from 1 up to 500. And once that sensitivity analysis has been done, we use TSM polygon to populate the data in the model domain. So we reviewed so many resources regarding the dispersivities, especially in South Florida area. Some of them usually 1 to 5 meters used by USGS in some areas, and 200 to 500 feet by Geotrans. They just simulated in 1986 around Highland Beach. So, so those values, once we did sensitivity both global and local, are used to plot this data for the 5 layers. For longitudinal dispersivity, we determine using and use the longitudinal dispersivity to determine the vertical dispersivity by multiplying factor of 0.01, and for the horizontal dispersivity, we multiply the longitudinal dispersivity by a factor of 0.1. Again, these values, we did some sensitivity analysis varying from 0.01 to 0.0.
Yeah, I have a question.
Wait,
I know, please.
Yeah, so first sentence on the slides, what do you mean by applying ranging from 1 to 100 using the testing polygon? I didn't catch that.
so what it means is we had ideas what values would be appropriate to use for our dispersivity value. And we used, let's say, a global value of 1.
Okay.
And then we use a global value of 5, global value 20, 100, 150, up to 500.
Okay.
So depending on the dispersivity value we used, the model responds, we look at how the model responds to each global dispersivity value. Wherever we found the model is working well, we capture that data. We compare all the dispersivity values used, and wherever it works better, we'll just capture it. And that target value will be assigned a specific dispersivity value. So wherever, because we have our hydrographs, we just look at the hydrographs. So for a given dispersivity, if it's doing better in certain areas, for that target set, we give it that value.
So let me ask, so how do you decide those testing polygons?
The test polygon, I mean,
How do you call it?
test polygon, this is how it works. If you have different values,
Right.
it connects the two values and creates a line which is cutting between the two lines.
Right.
Yeah, so that's how it
So
works.
those are the polygons you draw based on the model, the previous model?
Based on my dispersivity values. I say, okay, a given target has dispersivity, let's say red is 500. as you can see here. So I have some targets around here with the 500 value. With the green one is only 1. So I have some target values with the value of 1.
Okay.
So I just, like it's about, back then it was about 1,200 target points when I started with
Observations.
observation data.
Observed water level.
Yes.
Location.
I mean, the
Well,
dispersal.
no, not observed water.
No,
Observed
so
water quality,
basically he's saying is that we had our calibration locations, right? For our water quality.
Okay.
So step one was set a uniform dispersivity of 1.
All right.
Then you look at your graphs of water quality over time and you say, okay, this set of 50 wells responded like were better calibrated. It's a sensitivity one, right? So better calibrated with dispersivity value of 1. So spatially, he said those 50 wells are located here. We want dispersivity values of 1 for those. Then he did the next run of 20 and did that for each of the 5 values, and then used Thiessen polygons to say, okay, these wells are in layer 1. Here's the ones that wanted 1 for dispersivity, 20 for dispersivity, so on and so forth. Use Thiessen polygons to create the array for layer 1.
So basically, you draw this polygon based on the previous calibration results.
Yes.
To look at what the parameter distribution looks like.
Absolutely.
There's nothing to do with really what previous model.
No.
Because I know almost model just use one value for the whole aquifer because there's no measured value.
Correct.
It's just value calculation. So that you assign 1 to 500 as a
Yes.
static number
Yes,
to run, then to check and see which one the best.
exactly.
Yes.
Well, that take a lot of time. To do
Yeah.
that.
Yes, it does. And it's a manual calibration. It takes really. Right.
And then, it's a little weird that there's such sharp drop off, like cliffs,
Yes.
basically, right?
Yes.
So I don't know what it would look like if it was looking at a plume coming across there, how that would even.
Yeah, as you can see here, wherever you have so many target or observation points,
Yeah,
you have so many data and they just, cut small pieces.
right.
But wherever you don't have data, you can see it just by open. And they are just, as you said, with sharp calibration.
And I think going along with Ray Jing's comment, it may not even be that important, so. It's hard to know.
So what's your starting point? What's the starting usual?
I started with 1.
Use 1
Yeah.
foot, 1 meter.
1 foot, yes.
1 foot.
1 foot.
Okay. So what's the end up? What's the max number?
Maximum number is
It's 500.
500.
Okay, I see.
Yes.
So there were there was a literature value, and then there was the geotrans report was in the Biscayne Aquifer in Ellendale Beach. And they arrived at a longitudinal dispersivity somewhere between 200 to 500. So those are the brackets.
Yeah.
1 to 500 were the values that were obtained from the literature, and then your gallon landed somewhere between 1 to 500 for every one of the areas there.
And just to go on to, what do you mean so longitudinal dispersivity multiplied by 0.1 to get a horizontal?
Yes,
I don't
So
understand that.
yes, suppliers that input in the model, they're just 2 values in there, 1 for each layer.
So the step we're missing here is longitudinal to transverse.
Yes.
The first thing you need to do is go to transverse dispersivity from longitudinal, and then there are 2 components of transverse, vertical and horizontal.
What do you think about that? I think longitudinal. and
That's
horizontal. are-
MT3 default value. From 10 to 1, 100 to 1, that's the. Well,
Well,
people
yeah,
have
yeah,
nothing, so they just conceptually say, okay, the transverse is 10 to 1.
Oh, yeah, totally agreed, but isn't the the longitudinal and the horizontal the same?
In surface water is same. In surface water, it's just you put plume in the water like a swimming pool.
Yeah.
All directions same.
Isotropic,
Only in groundwater.
Yeah, I know, I recognize that there's a strong 10 to 1 horizontal
Yeah.
to vertical difference in the transmissibility. Longitudinal, I see, longitudinal and transverse, right, okay. There's 2 horizontal ones, basically. Sorry. I got so used to doing column experiments.
So you do find any thing you want to change that default value from 9 to 3D to 10 to 1 to 100 to 1?
So
Yeah,
you're
we
saying
did-
that's good.
Yeah, we did some sensitivity analysis
Okay.
on those factors, but we found that's better ones.
So I think, and we're gonna get into this a little bit, but we've got the watershed structure flow calibration going on. We have wetland water levels going on. We have water levels and monitorables going on, and we've got the water quality going on. And in order to get the water levels correct, you can turn your hydraulic conductivity, horizontal and vertical, to a certain extent. And then, but at the same time, you've got wells that have water quality. If you mess with the horizontal and vertical hydraulic conductivity too much to try to get better water quality calibration, you can start throwing your water level out of calibration.
Right.
So dispersivity was one of the knobs that we could turn without affecting as much the water level calibration. So that's where we landed, is that we've got all these things going on at the same time, and I use the phrase whack-a-mole a lot, is and staff had to go through this, is that once we landed at a certain point in terms of the vertical and horizontal hydraulic conductivity for the water level calibration, we couldn't mess with it too much without throwing the water level off. So we were stuck with, what are the other parameters that we could achieve, that we can vary to try to get better water quality calibration, and dispersivity and effective porosity and others are the others. So that's why maybe in other modeling efforts that you've done, perhaps you haven't had to change the dispersivity very much.
We never changed that.
Right, but we did, because if we changed the vertical or horizontal hydraulic connectivity too much, then all of a sudden the water levels will go off, and that's the whack-a-mole thing. Is like at some point we had to kind of lock in the K values and vertical K to a certain range, and we could vary it a little bit. But when that wasn't enough to get the water quality calibration, now we've got to go to these knobs, the dispersivity and effective porosity knobs, to try to get the best water quality calibration without throwing off the water level calibration.
Yeah, a lot of times want to go
Yeah.
back to rerun a flow model because the
Yeah.
dispersivity. But I never, kind of was surprised to see your model is so sensitive to this number, so that you can
Yeah.
try to draw so many polygons.
It may have been less, drawn, you might draw your eyes less of the big hitter.
All right. So the second parameter for as an input to the transport model is the effective porosity. So they're determined based on previous studies and previous numerical models, specifically around Biscayne aquifer. So most of the studies have been done by USGS, and one by Rankin et al. In 2008. He established effective porosity values of between 0.04 and 0.41. And another study by USGS again, they found a value between 0.08 and 0.4 for effective porosity. We know the total porosity is much higher, but the effective porosity is never been like almost 0.4. So as you can see, it follows the pattern of the hydraulic conductivity, which is pretty obvious because the permeability is dependent on the hydraulic conductivity. So that's somehow related. To the material related to the effective porosity, and then that's directly related to the hydraulic conductivity. So
That can be especially, I don't know how much clay, probably not much clay. You want clay there, that sediments can be questionable, and because the K is low, but the porosity is high, effective porosity is low.
yes,
And this is kind of a complex correlation.
That's
then.
that's good.
So to the other area, what do you do other than the Biscayne? You have the value from UIDS study.
Again, we did similarly some sensitivity analysis, by the way, on effective porosity by applying those values. We just wanted only the range.
Okay.
So we went to apply these values. We used that range. So the range was more important for us. Once we fixed on that range, we just landed on those values.
So those
Just
are
right here.
uniform value
Yeah.
for the others.
Yes. So in some places, the green is about 0.2. The blue lines are about 0.3, and the dark brown are 0.4. So that came up with some sensitivity analysis, as we did, for others.
So wishing you were saying earlier that a lot of modeling you've done, that the dispersivity values were pretty much constant.
Yeah.
What we found is the effective porosity, it wasn't that sensitive, so we
Yes.
just set it at the uniform value. In other words, we twisted this knob to try to get better water quality calibration, and it really didn't matter very much. So we just landed at a reasonable value. 0.2 is,
All the effort is just to get 5, 6 wells to be calibrated. Look, we have quite a number of wells. So as long as it helps us, then just capture them.
It's hard to do the solid transport modeling because a lot of numbers are not sensitive. So you, no matter what you
Yeah.
do, it's, so that's why I suggest you set initial condition right.
Mhm.
That's make a lot
Yeah.
easier.
Yeah.
Otherwise, you try to twist them back, do the calibration.
Yeah.
It's very hard.
It's very
Yes.
difficult, yeah.
The last one is the source and sink mixing cells. We're fixing on southern Miami-Dade area where there is high or hypersaline areas, and the TDS value ranges from 40,000 to 80,000.
That's the IPL. Is that FPL?
Yes, it might be. Yeah. I don't-
Oh, sorry.
No, you're good.
All right, Anish.
Yeah, I'm doing a project with the FPL.
Yeah.
Oh, okay.
Yeah, so that's they've got hypersaline water, which we had his observed data for.
Yeah.
So we set that for the SSMs. That's the only location. I think last time when we met, we had SSMs in other locations too, but where we landed was just in that area.
I see. Yeah, I'm reviewing their progress on the remediation on that
Yeah.
room. Yes.
So the part that I think we all want to
Has
talk
it
about.
repeated any?
They control the shallow part, so okay. Yeah, so it's nothing secret because the reports you can find online. So the shallow part, they retrieve that, but deep part, basically,
I'm
almost
thinking
nothing happened. And so that's very unfortunate, yeah, so because the density is so high,
Mhm.
you're just sitting the bottom of the aquifer, no matter what you do. So that's so it's tough question. So,
So I think the part that we all kind of anxiously want to present is the model calibration. So our approach, which I think has been the same pretty much through this process, is to calibrate ECSM. Phase 1 is the manual calibration, but we, as Jurgelim's been mentioning, we've been doing a lot of sensitivity throughout the process. But we started with our water levels, getting them kind of pseudo calibrated. Then we moved on to water quality, got it kind of pseudo calibrated, checked the structure flows, realized that we had to tweak the river conductance. But then if we had water levels near the rivers where we tweaked the conductance, we had to go back and check that. And as Pete mentioned, it's kind of a whack-a-mole thing, which is kind of you'll see throughout the rest of this presentation is we really had to make a lot of judgment calls, right? And we really had to kind of keep in mind, what is the objective of ECSM? What are we going to be using this for? And is it good enough? So that's phase 1. Phase 2, which is what's going to happen here shortly, is that utilizing pests to do the global sensitivity analysis. That basically will give us the confidence to say, okay, yes, this model's, we've calibrated the model, we're using pests to say it's as good as it's gonna get. So the water level calibration parameters that we used are, pretty typical: aquifer horizontal and vertical hydraulic conductivities, storativity. We had variations in recharge and ET rates. With our ET recharge program, it gives us the flexibility to do that. And then pumpage distribution by source and well field. This is actually a critical thing that we struggled with a lot. Our public supply pumpage especially. And then river and drain conductance. River conductance, especially for the structure flows. And our water levels were calibrated again on a daily basis. For the wetland calibration procedure, our parameters are CADLIC values and then the extent of the wetland areas. So what we noticed was those contiguous polygons. We were making sure that the areas that were supposed to be wetlands are actually captured as wetlands. one of the problems that we had was land use. I think it was one of the years of land use, they classified wetlands differently. So when we use that to determine our wetland coverage, we missed like a huge chunk of Ian. And so it's like, we know the Everglades is a wetland, we need to get it in there, so we updated our wetlands coverage. And then specific yields of the muck is a very sensitive parameter. It prevents too much water from ponding on those wetland cells. And our wetland stages were also calibrated on a daily basis. And then for the water quality calibration procedure.
Thank you again. So, for water quality calibration procedure, this year, like the parameters we set and we, as I just mentioned earlier, one of the parameters was longitudinal dispersivity, using the sensitivity analysis, say horizontal and vertical dispersivity, which is again as a fractional factor of the longitudinal, the effective porosity boundary condition conceptualization. What it means is we use the intracoastal, the Central Sea estuary, and other estuaries as rivers and apply it with a flex of the same water quality value of those intracoastal water quality data. So the river that with that flex in water quality has stabilized our model and performed better. The other one is initial water quality arrays. Anish mentioned it earlier. There are trapped connects, but water beneath the Everglades agriculture area and water conservation areas, as well as in Lake Okeechobee. So we have to go back and tweak those initial water quality arrays. Anish just, I think she went at length. And finally, water quality was calibrated on monthly basis. You all know it doesn't respond on a daily basis, so we have to calibrate it on a monthly basis.
I remember at the beginning, talk about the tidal, it's on a daily basis, right? Because the tidal is on daily basis, then you calibrate the target only on a monthly basis.
Yes.
Well, the heads are high. About their pattern, so as a boundary condition.
But I mean, the salt floods,
Yeah.
the salt water coming into the model is on the daily basis.
It is, and because we have the sea time very comprehensive in layer one, we're emulating the ocean essentially in second, it will allow the water quality flow.
Yeah, so I know most of the places you probably don't have a lot of water quality data, but if you do, you average them up in the months as a target.
What was?
So if you have a
We take the last observation within
Uh-huh.
that month and compare it to the
the
last
last
value.
one, last value in
So
that month.
let's say if they only reported like May 15th, and that's the last time they reported, we
Okay.
get that value and compare it to the end of. month.
Okay, if you have
August,
the November first, that will be the.
That would be
represents the last.
Yeah,
So you don't average that.
no, there's usually not enough points, it'll be like one.
I know, it's a unique case, yeah.
Yeah, and sometimes the data is quite sparse, you know.
No,
Yearly basis.
if kind of for one per month, that'd be lucky,
Yeah,
right?
exactly.
Yeah.
All right. So, again, here on this slide, I'll just demonstrate how water level calibration helped us to calibrate water quality. So, as you can see right here on the graph, the blue line, I'm sorry, the green line is observed data. Whereas the blue line represents the simulated water quality when the water level was not calibrated. And the red line represents the simulated water quality when the water levels are calibrated better. So in short, improving the water level calibration has helped us to calibrate the water quality.
Which is unexpected. That is expected.
Makes sense. You know what they used to say, get the water right, right?
Yes.
Which is also why we started with water levels and then moved on to water quality.
All right. Good morning, my name is Brian Martinez, and I'll be going over the water level calibration results. So on your right, there's a map of our 666 water level targets. So our water level calibration goals, for our mean absolute error to plus or minus 1 feet. Mean absolute error, 50% of wells with MAE less than or equal to 1 feet. 80% of wells with MAE less than or equal to 1.5 feet. So for our water level calibration statistics, we start with our overall ME. So that's a negative 0.19. For our calibration ME, that's a negative 0.16. For our verification ME, that's a negative 0.35. For our wet season, negative 0.33. And for our dry season, negative 0.06. So for a percent of wells with MAE less than or equal to 1 feet, it's overall 57%. Our calibration is a 56%, and our verification is a 72%. For our wet season, it's a 56%, and for our dry season, 59%. For our overall percent of wells with MAE less than or equal to 1.5 feet, we had a 75%. So we almost reached our calibration goal. For our calibration, we have a 75%. For our verification, we have an 82%. For our wet season, 74%. And for our dry season, 75%. So our overall statistics are calculated for a full model stress period of 11,688 or 1985 to 2016. Our calibration goes from 1985 to 2012. And our verification is a more recent record of period. So that's from 2013 to 2016. So a reason why our verification statistic is doing better than our overall in calibration is because we have a better input for our rainfall and pumpage, so better or more accurate. So overall, we have a better quality for our input data.
Okay, so as Brian kind of pointed out, the key here is our verification period. While we discussed the pumpage, the historical flows through the park, all of those things are of better quality during our verification, which is why you see much better stats during the verification period. So looking at our overall calibration maps, we refer to these as our heat maps. You can see all the wells in layer 1, all the wells in layer 2, and all the wells in layer 3. And kind of looking at the legend, everything that's a circle is over predicting. Everything that's a triangle is under predicting. And the reds are the ones where the mean error is either greater than 3 feet or less than 3 feet. And then if you look at the oranges, it's between 1.5 to 3 feet. So what we did was when we put these maps together, we kind of wanted to look for areas that were glaring in terms of, hey, I have a pocket of area that's not well calibrated. And what do I do about it? Right? So what stood out to me is if you look at this, it's hard to control this pointer, but the northern Martin County, like basically between the St. Lucie and Martin County line, where the Stewart Wellfield is, we had a really hard time calibrating. And we did a lot of sensitivity runs, trying to figure out, is it hydraulic connectivity, like what's going on in that area? And it's because it's wells. We have pumping wells on top of monitoring wells, surrounding the monitoring wells, and it was just very, very difficult to calibrate this area. So that was kind of a noticeable trend. We also have areas, if you look at Fort Lauderdale, we have an area right here and an area down to the south here. But it seems like it's more pockets of areas that may not be well calibrated, but sitting right next to a well that is calibrated. So I couldn't make a lot of changes without throwing off the wells that were calibrated. So again, what do? It doesn't make sense to go in and change cell by cell a hydraulic connectivity. That's not justifiable. So we were like, okay, what other calibration parameters do we have? And so Jurgen just did a test run on the pumpage, and said, hey, Anushi, let's turn that knob and we can bring all these wells into calibration. And we said, yeah, but that's the only historical data we have. We can't justify changing pumpage that's been reported to regulation. So it was a hard call for us to kind of land where we did, saying, hey, our goal was 80%. We're at 75 during calibration. It's good enough, right? We're performing better in the verification where we're at 82% because our data quality is better. And so that's kind of how we went through this process of the calibration. Same thing for layers 4 and 5. Again, you see in layer 4, we've got that Stewart area sticking out. But it's just the nature of the data that I have. You know, so we really tried to go in and look for those types of pockets and see what we could do to calibrate. But this is kind of how we ended up, knowing that we're close to the 80%, just a little bit short, but our verification looks really good. So that's the water levels. I'm going to hand it over to Brian to start the wetland gauges.
So for our for our wetland calibration results, we have our 187 wetland gauge locations shown on the right. Our wetland calibration goals start with our mean error of plus or minus 1 feet. Our mean absolute error, 50% of gauges with MAE of less than or equal to 1 feet. 80% of gauges with MAE less than or equal to 1.5 feet. So for our wetlands statistics, starting with our overall ME, 0.85, our calibration, 0.90, our verification, 0.49, our wet season, 0.65, and our dry season, 1.0. For our percent of gauges with MAE less than or equal to 1.5 feet, our overall is 50%, our calibration is 49%, our verification is 60%, our wet season is 55%, our dry season is 48%. For our overall percent of gauges with MAE less than or equal to 1.5 feet, we have a 68%. For our calibration, a 66%. For our verification, 79%. For our wet season, 71%. And for our dry season, 66%. Comparing our wet season and our dry season, we found that we had a bias in our dry season. So that's the reason why it wasn't performing as well as our wet season.
So looking again at our heat map for the overall, if you remember, I want to say it was maybe 2 meetings ago, we saw this area wasn't as well calibrated. And we went back and those days, we went back and looked at the boundary conditions. And back then we had GHB cells along the western edge. And that was the reason why these wells weren't calibrated. We no longer have GHB cells. But what we believe is for this area that's clearly not performing as well as we would like, what we believe the reason is remember the RDF coverage that I had, where we had RDF cells pulling water from Conservation Area 3 and routing it into Everglades National Park. We don't have great historical information for that. We're assuming this is how it was operated back in those days, but we don't know for sure. And so we're seeing a trend of the fact that we're over predicting. That means we're injecting too much water into those wetland cells. And then being a wetlands coverage, it's overland sheet flow into this area, basically at a higher amount than we would expect. Now, when we looked at this, we said, okay, we've got to kind of decide, what are we using ECSM for? What areas do we care about the most, right? And this model is going to be used for water supply planning purposes. We care about the areas in the urban areas. And we see that we're really well calibrated on the edge of the park next to urban Miami-Dade. So we said, okay, are we as good as we want to be? Probably not. But is it good enough to use for water supply planning? Knowing that the edge of our model domain, if you look all through the edges of where the Everglades National Park borders our urban areas, yeah, we're very well calibrated in those areas. And so we made the judgment call to say, okay, we're happy with where we landed. yes, we could have improved some conservation area flows going into the national parks, but that's not what this model is gonna be used for. We're not, like, wishing one of your comments was, you're not capturing the water moving through the canal network. We're bucketing it over. So we're not gonna capture the intricacies of the system, right? But we had to say, okay, yes, we're not, it's a limitation, but we're also not gonna be using this model to predict anything in Everglades National Park. So we were comfortable with the fact that our wetland gauges look the way that they do.
Can I just add, so I'm not sure you explicitly said it, but when we tried to improve the wetland calibration in the wells that are not calibrated, in the stage gauges that are not calibrated, we would throw off the calibration to the east, which we did not want to do. So if we had to make a judgment between which area do we prefer, or do we think it's better for water supply planning purposes to have the best calibration? And it was right along the edge of the urban boundary, and less so in the footprint of the Everglades system. So, but when we tried to improve the area that's in the orange and red, we tried to improve that, we threw some of the green stations out of calibration. So that's where Anushi was talking about, is we had to make a value judgment of which area is most important to us from a water supply planning perspective. And it's certainly closer to the urban boundary as opposed to deep in the heart of Everglades National Park.
And actually, it wasn't just the wetland gauges, but if you look at, I've got a lot of water level monitoring wells right on the edge too, and they're all nicely calibrated. So I really couldn't afford to throw off all of this area in layer one, right? That was the part that we cared about significantly, capturing this urbanized area. So, you know, it's not as pretty as we would like it to be, but you know, we had to just kind of say, okay, it's good enough. It's good enough for what we're going to be using the model for. And now the water quality. So our water quality calibration goal, again, we looked at those individual observed data points. We classified each observation point into a bin, and then that bin determines the error bands that we use to determine if that observation is calibrated or not. And then for every well, the series of observations that we have, where our goal with 80% of all those observations should meet this error band target. And we wanted 80% of those wells to then be considered calibrated. So we also had a soft calibration metric to say, well, out of all the observations, regardless of what well they fell into, how well calibrated are we? Just get an idea. That way we know, is it the fresh water that we're calibrating really well? Is it the saline conditions? What are we looking at? So here on the left, we can see all the water quality monitoring wells that we actually ended up with in the calibration. So we're trying to calibrate all of these wells. And it was originally, I think when we met previously, it was like 800 or 900 wells. It's not that many right now. We actually went through and said, if we only have, 5, 6, 7 data points, we can't calibrate to that. It's not possible. So we went through, did a lot of cleanup. We also looked at things that were just kind of anomalies. We had some data that was in layer 5, east of the front, showing us like 200, 300 milligram per liter in TDS. And we knew if it was east of the front at the base of the aquifer, that's definitely not correct. And what we noticed is if you look at the actual water quality monitoring stations, most of it comes from regulation. So we were like, okay, are these USGS monitored wells, or who's actually collecting the water quality data? One of the funny stories that we've had is we've actually had a permittee use water quality. He reported his chlorides, but the way he got chlorides was to use a pH test, like for a pool. And he went out and pulled that, and that's what he reported on a monthly basis. So we had to do a lot of data cleanup to look at this. And what we ended up with is we wanted utility data, and we wanted like USGS data and our own district data. We eliminated a lot of data points based on what we consider the quality. So here's the actual results. We had again 578 wells overall. For the verification period, we actually have less wells because we're monitoring less in the current or the from 2013 to 2016, we have less wells that we're monitoring. But overall statistics, again, as Brian mentioned before, that's for the entire period of record. The calibration is 1985 to 2012, and the verification is 2013 to 2016. So although our goal was 80%, where we are right now overall is 70%. Our calibration is 71%, and our verification is 68%. Now you may be wondering, with the water levels and the wetlands, we actually performed better in the verification, whereas the water quality, we're doing a little bit worse. And the reason for that is if you look at some of the water quality over time graphics, you'll notice that we're capturing water quality well, but we're capturing it either too soon or too early, or too soon or too late, right? And so what that means is if I have that time lag, then immediately everything shifts and I can't catch up later on. So that's why the verification actually looks a little bit worse. But if you look at the heat maps, again, you'll notice like trends in areas. Again, looking at like the Stewart area, you see some green mixed in with some red. Layer 3, you see a little bit more red, things like that. And what we'll notice is that most of our wells are co-located again with a well that's calibrated and then it's paired with one that's not. So how do you calibrate something when you have 2 cells over a well that's nicely calibrated compared to something that's just, it's not calibrated? But then what does not calibrated mean? Right? So that was something we spent a lot of time looking at this, trying to figure out, okay, it's not calibrated. Does that, like, what does that mean for the model? Right? Is it unable to capture things? What's going on? Like, why are we not meeting this 80% goal that we have? Same thing with layer 4 and layer 5, although layer 5 looks, in my opinion, pretty good, right? Where we're seeing the base of the aquifer and where you know intrusion to occur. It looks pretty good. We've only got a couple of wells that are out of calibration there. Same thing with our soft calibration. So if you look at the actual number of observations in that first bin, the 0 to 1,000, we have 82,512 observed data points. It's way more than any other bin that I have, right? And in that section, we're calibrated 73% of the time. So that means in the bin with the fresh water, with the smallest calibration error target, which is plus or minus 375 milligram per liter, 73% of the time I'm capturing that. And that was critical for us because that's where saltwater intrusion is going to occur, in that fresh bin. What our goal is with this model for when you think about the objectives, I want to see what areas are currently fresh and over the 20-year to 50-year planning horizon may become susceptible to saltwater intrusion, right? So that's going to be able, that gave us comfort, basically saying, hey, this is the bulk of our data. We're calibrating it well. Like this was critical for us to kind of know that. But again, there were those areas like Stewart. What's going on? Why can't we calibrate it? So if you zoom into Stewart, and this is actually a screenshot from the stats view. I think we provided a link to it, which is a great graphical interface. You can zoom in, pick whichever layers, whether it's water levels or water quality, and you can see, using the legend, how well calibrated the wells are. Those in green are greater than 80%. The limeish color is 60 to 80, orange is 40 to 60, and the reds are less than 40%. Right? So when we looked at it, we said, okay, we've got these wells that are kind of in red, but off to the sides, we have wells that are in green. Now, these guys are inland of the front, right? Then we have on this side, we have a red, but we also have a green. So it's not like the entire area is not calibrated, but we do have wells that aren't, right? So they're co-located next to green wells, but also the blue coverage is the public water supply wells. And I don't have pumpage for those. So what do I do when I'm using a public supply well that's a productive well? It's also my water quality monitoring station, but I don't have pumpage data for it. I'm estimating that. It becomes really difficult for us to calibrate those wells. And so our initial thought was, okay, let's just get rid of the productive wells that are also used for water quality because I'm estimating that. That was more than 350 points. I would be left with like 100 water quality stations that I'm trying to, calibrate to across this massive model domain. So we thought about it and we were like, we can't do that. So then we said, okay, we may have to live with the fact that our stats are what they are. We know that surrounding areas, like perfect example, the green well that's not a production well is the one that's calibrated. Right next to it, the two reds, those are production wells. So it really kind of helped us like put the hammer down where that pumpage is critical and we're estimating it, right?
So the district require them to report the pumping rate?
The district requires, it's a part of their water use permit.
No.
So, but that only, I think, so Alicia and I both worked in regulation before kind of coming over here. And I think it was 2010, right, that we started cleaning up the data.
Yeah.
Prior to 2010, there wasn't really a QA/QC check on what was submitted, which is why we started using the pumpage data back to 2008. But sometimes we would look at it and we'd be like, it's kind of suspect, and we decided to, whether right or wrong, we decided to honor that pumpage. So, for us, it was kind of critical that, okay, we're a district agency, we have data in-house. We can't really say, hey, we don't believe our own data that's in-house. So we decided to honor that, but then we're left with something like this. So it was hard,
You estimate the pumping rate based on the pumping rate?
So we estimate from, let's say if you're taking 1985, right?
Mhm.
We have regulatory records that show per month how much each permit is pumping. Now, a permit can have 3 well fields, it could have only 2 wells. But I don't have any information about what's coming out of a well field or what's coming out of a well. I just had to evenly distribute. Right? So that, I believe that even distribution is what caused this problem, right? If you're looking at, not necessarily Stewart, but some of my other utilities, they may have a east well field and a west well field, and I just evenly distributed. So it could be that they used the eastern well field more, then intrusion moved in, they switched the west well field, intrusion moved out, and I'm not capturing any of that, I'm just evenly distributed. So, there's a lot of nuances here that kind of made it so difficult for us to calibrate this model. I think water quality calibration is difficult in general, but this made it like, it was a lot.
Yeah, and have you looked like at any cross sections? Like, is there upconing going on in these places? I know it'd be a little too much to look at it through the whole model, but I mean.
We don't really see any upconing coming in. For the most part, these areas are relatively fresh. We don't know, the model's not simulating any upconing.
And so the line you're showing on there, is that derived from the model?
No, the line that's actually the StatsView application that Jose derived. It allows you to bring in the isochlor line.
Yeah.
So the red line is current.
The pops up with the most current one, but it has all the estimations of that score from.
So you can kind of see the isochlor moving, like the intrusion line moving in.
It's the mapped 2020, most recent mapped 2024 version of the interface.
Yeah.
So Wellington was another situation. So we looked at this and I was like, there's 1, 2, 3, 4, 5, 6, 9 wells. 9 wells, which don't really seem like a big deal, but when you're trying to reach your calibration goal, getting 9 wells, it helps, you know, move up a couple percentage points at least. And so we were looking at this and we're like, why is everything red? It just looks bad. You know, Stewart, at least I had some wells that were calibrated. Wellington, I don't have any. And so we said, okay, all of these wells are pumping wells. And then we looked at the water quality over time graphic. And we said, okay, it's not really initial conditions. We're kind of, you see a decreasing trend, the model showing that decreasing trend, but it's almost like it's just kind of shifting, right? And so again, Jurgen loves to do his sensitivity runs, and he's like, Anushi, if we reduce the total pumpage from this well field, it's like a snap of the fingers. You're immediately calibrated. So it was, and he actually did it, and he put it into the well package, and then he came into work and he's like, I got the wells calibrated, we're at like 77%. And I was like, that's amazing, what'd you do? It's like, I tweaked the pumpage. And then we made the call, we're like, can't do it. We have to go back. And so we lost all of those wells again, the second we honored the pumpage. And so it's like, we're stuck with kind of what we have, you know? And so just that simple modification could have brought all those wells into calibration. But because we as a district decided to honor our pumpage records, you know, we're unable to calibrate this area. So then our thought was, okay, does that mean we can't use the model in Wellington? I don't think so. I think what we're saying is we don't have good historical record. We're showing the trends the way that it's historically been observed. And when we move into the scenario runs, we're not relying on historical information anymore. We're relying on a 2020 demand that's coming to us from the planners. They're going to be giving us how much Wellington's going to be. Well, actually, 2020 is how much each well was actually pumping by the utility. 2045, the planners coordinate with each utility and say, hey, this is how we're going to be operating our well field. So we're no longer kind of guessing or estimating what they're going to be doing. And then not only that, but we're only looking at a difference. So if you're only looking at the difference in the delta there, then you can use the model even though these wells aren't calibrated, right? So that was kind of the thought process that we went through when we were trying to calibrate the water quality. And so again, we had some limiting factors, things that kind of limited how well we could calibrate the model, right? The first one, and one of the things that I didn't really mention, is if you look at Miami-Dade, right? Every area that we had those greater than 50,000 feet per day K values, we really struggled, right? Our water levels looked really good, but our water quality did not. And what we found is the water quality actually, it wasn't sensitive to dispersivity, it wasn't sensitive to any water quality parameter. The only thing that could get that water quality kind of calibrated was to modify the K value. But we have documented APTs and plenty of literature that says, no, this area has that kind of very high transmissivity, right? So I can't deviate from that. There's just no way. You know, when Jurgen was showing the aquifer parameters, it was, yeah, we manually tweaked things locally, but we always went back to make sure we weren't kind of deviating from those APT data points. And so we ran into this situation where we know the transmissivity is high, we know our water level is calibrated, but even though we have those two things, we cannot calibrate the water quality in that area, right? And it's because of that, it's not really Darcy flow in those areas, right? So we had that as a struggle. The second, and I think probably the biggest limiting factor, is the pumpage. So we chose to honor the reported pumpage. If we had chosen to modify it, we could have calibrated and met that 80% calibration goal. We just said that this is the best information we have. How can we justify when we house the regulatory database, we're saying this is the data. How can we say that on one stand and then on the other side say, oh, we have it, but we don't believe it, so we didn't put it into the model. You know, we couldn't do that. And with that, we would have been able to calibrate not just the water quality wells, but even the water levels. If you zoom in with using Jose's stats view to the areas where you see red for the water levels, those monitoring wells literally are surrounding well fields. And that's the trend, right? That's every time we looked at areas that had uncalibrated monitoring wells, the trend was there were public supply wells right around it. And so that was a big limiting factor for us. And then of course, you know, it's a regional model, 1,000 feet by 1,000 feet grid size, local heterogeneity is not captured, right? So we do have some limiting factors, but again, when we think about the objectives and looking at water supply planning and looking at difference runs, these things don't limit the model in being used for that purpose. And so now yes.
Yeah, can go back. Yeah, I'm interested in the first one.
Yeah.
So have you verified that statement based on the Renault number or something to see how fast this non-Darcy flow?
We have not. Basically what we did was we looked at a lot of literature, right? I know, like with Martina, you've worked on the non-Darcian flow and looking at parameter estimation, right? It's something that has been discussed for the Biscayne aquifer. And how do you handle estimating the parameters, and how do you handle the fact that it has some non-Darcian flow, like issues in that aquifer because it's so porous.
Yeah.
You know?
I mean, basically, there's a big holes there, so
Yeah.
the water flow.
Yeah.
So that's.
But no, we didn't consider the Reynolds number and things like that.
I see.
But it really makes transport go wonky when you get those higher. Yeah.
No, I just I saw the report of how fast they can be in the filter pass, but you know, but when we all the average out, so we normally ignore that.
Yeah.
Because we assume that's the porous media.
Yeah.
We don't see any holes,
Right.
and so that when you average out like 1,000 feet by 1,000 feet by 30 to 100 feet, see, that's big piece of cake. That we normally don't care about that.
Yeah.
But that's interesting, yeah, so you mentioned that, I know, so I just curious about.
Yeah, I think for us, even though it's a regional model with 1,000 feet, I'm using that specific well as a monitoring station,
Right.
you know?
Right.
And so I think, you know, looking back, maybe an option would have been if we know that this is in an area specifically, you know, the well is specifically in an area that has non-Darcian flow, maybe we shouldn't have used it as a monitoring station, right? But we kind of erred on the side of we're using all the wells unless it was something like a data, like a survey elevation issue or something like that. Other than a known error or issue with the well, we used everything. And so we're unable to capture some of this stuff. And so, you know, yes.
Yeah, so it's quite interesting because I mean, the aquifer performance tests, as you call them, you know, like Fish and Stewart is one that I looked at a lot, and most of those, the conclusions there are that the permeability or the hydraulic conductivities are like above some value due to the limitations you're talking about here. So I'm kind of wondering, like, did you have to, when you're talking about trying to make adjustments to the Ks, were you going to have to go lower or higher to try to match the water quality better?
The water quality preferred a lower K.
Interesting.
Yeah.
Okay. Yeah.
I mean, and it was a very apparent, like, we would see some wells that were, I mean, it almost looked like a parabola. But the second, if we knocked down the K value, it would just match almost identical. And it was like a quick switch, but how do I justify not going with Fish and Stewart and things like that?
Yeah, right.
I can't. So, you know, we said it is what it is.
Yeah.
So, you know, it's given us a lot of sleepless nights, to say the least.
Now on to our structure flow calibration results. So on your right, we have our 4 calibration target basins going from north to south. And within those, we have our calibration, surface water flow calibration structures. So we've identified these 4 joint basins from our sub watersheds and basins, and they were joined together based on drainage areas to create the joint basins. Our calibration goals for our structure flow calibration starts with our coefficient of determination, so our R squared, and that's greater than or less than 0.4. Our Nash and Sutcliffe is greater than or less than 0.4. Our deviation of volume is plus or minus 15%. So here for our joint basin 1, we have an image showing our historical flow in black and our simulated flow in red in cubic feet per second. And we have, so for our joint basin 1, we have a shorter period of record starting from 2009. And our NSE is a 0.84, R squared is 0.85, and DV is negative 11.9. For joint basin 2, we have a NSE of 0.78, R squared of 0.79, and a DV of negative 5.3. And for joint basin 3, we also have a shorter period of record from 2012. And that's a NSE of 0.50, R squared of 0.60, and a DV of 12.1. Finally, for our joint basin 4, we have our NSE of 0.64, R squared of 0.67, and a DV of negative 7.6. Now back to Anusha.
Anusha, can you cover real quick the reason that we don't have a fuller period of record for the joint basins for?
Sure. So this is basically like a water balance, a water budget approach, right? So one of the things that we knew we had to do is we had to have historical information, both outflows and inflows, to figure out how to calibrate our canal leakage or our runoff. So anytime we were missing, like we had some inflows but not outflows, then we didn't try to calibrate that particular month. So we focused in on the times when we had all the available historical data. Otherwise, it was too difficult for us to try to figure out if it's a leakage issue, is it a runoff, what needed to happen. So that's why you would think, especially in the CNSF, with the CNSF structures, that, like, for example, basin 3 would have more data, but we actually only had enough historical data to calibrate through from 2012 to 2016. Okay, so then we talked about the calibration goals in terms of metrics and water levels, water quality, wetlands, and structure flows. But you have to get the conceptualization correct. And the best way to do that is to look at groundwater flow vectors. So the first thing we did is, okay, where does the flow actually go? So this left-hand side graphic is pre-drainage. The water travels north to south through the Everglades and out mostly towards the west, but some southward flow too. But current condition is the water traveling north to south. There are releases from Lake Okeechobee, both east and west. And then we have flow going from Lake Okeechobee into the conservation areas, but then we also have flow coming out through the canal network into the ocean. So we wanted to kind of get that type of flow correct, right? So here we have groundwater flow vectors from layers 1 through 3. And overlaid with that, because at first when we looked at the flow vectors, we were like, why are these vectors going in kind of like pointing towards a location that we didn't know what it was? And it's actually because we have a pumping well there. So we overlaid it with our public supply wells to see if that justified why we had some changes in flow direction. But essentially what you see here in layer 1, you do see some larger vectors, and that's a representation of the overland flow from the wetlands package. So that sheet flow that happens from the conservation areas down into Everglades National Park is there. But overall, our flow vectors do mesh up with what we expect to see, right? The overall trend of kind of coming south, even in the lower layers, not just layer 1 where we have the wetlands package, but it comes south, it's going over to the east. They're also pointing kind of towards the wells as expected. And again, generally in layers 2 through 5, you'll have smaller vectors, but you'll see some larger vectors as they go towards like bigger well fields for utilities. And so here again, we have layer 4 and 5. Same thing, we kind of checked the vectors to make sure they made sense and we were comfortable with how it was. And so now I'm gonna hand it over to Jose.
And I'm just gonna briefly introduce you guys to StatView's application that we developed as part of the groundwater technical team. So StatViews is an application that's a web-based application that's part of a bigger pipeline of scripts and programs that Kevin Rothberg and I have developed, which basically pull the binary data from running the model, TDS values and water level heads, pairs them up with our historical data, as we've talked about daily or monthly, and calculates many of the statistics you guys have been seeing. And then StatViews is one of those programs that we made web-based that allows you to kind of view those statistics and interact with it. And I think it's better just to show. So this first view is kind of talking about the water level side of things. So when you open the application, you'll have a tab for water levels and for TDS. And it's just like, it shows the overall statistic goals at the top. And then you have your layer toggles. It starts off by default just showing layer 1. But you could turn on any combination of such. And it works just like any regular map where you can navigate, zoom in, zoom out. You could search station names if you happen to know the station names. And then when you click on the specific station, you get the station-wide statistics pop up, and then you'll get the graphics on the side. And then for the TDS, same thing, same concept. The only thing that differs here for the TDS is you'll get that orange error band that we've been talking about, where it's kind of a moving target depending on the bend that observation falls in. And so that's that orange band you will see there. And then here is just showing the overall controls. So like I said, you could toggle on any combination of layers or all the layers, zoom in, zoom out, switch between water levels and TDS, search specific stations. You have your legend down here. You can move that out the way to kind of make it as comfortable of experience as you want. And then you could toggle the lines on and off, download the images, zoom in into the graph. And then one of the things I do want to highlight that's a difference with the TDS side of things as opposed to the water levels is, like I already mentioned, the error band. But up to the right, you have the ability to turn on the I-score line that we've been talking about for different years estimations. As well, most recently, we also added the ability to turn on those public supply wells. So you could turn that layer on and see what they're at. And with that, I'll hand it back to Lisa.
I have a quick question. I played around with this. I think it's awesome. It was really great to be able to look around and compare the graphs here on the side. And I guess maybe this question will self-answer, but when I toggled between water levels and TDS, I thought it was going to work in the same place, but it would jump to somewhere else, basically a long way away. So that was a little unnerving.
That too.
Yeah.
Yeah, you didn't do anything wrong.
Okay, good. I'm glad to know. Yeah.
No, that's good input. I'll take that into account. There is 2 different streams of data
Sure.
that it's working with.
Yeah.
So by default, it is going to jump like that, but it is going to take into account if there is a way I can.
Yeah, it makes perfect sense. I mean, the same well doesn't have the data.
Yeah, that's true. We don't have the same one.
But we might be able to maintain a zoom extent.
Yeah.
Yeah, that would be.
Yeah, maybe.
Yeah. But it also happens like if you're just on layer 1 and you want to add in layer 2,
Yeah.
the second you add in layer 2, it resets and I'm like, oh my god.
Yeah, it resets everything because it resets all the filters in the data, but it's good input. I might be able to work around that. Alicia?
All right, so we've got at this point, and I know it's not in the agenda, but before we begin the formal panel discussion, we'll take a 5-minute break. So it's now 11:10, so let's plan to meet back here and we start sharply at 11:15.
Trying to put the plug in.
Yeah, exactly.
Oh, yeah.
Okay, welcome back, everyone, and we will now begin the panel discussion where we will open it up to the panelists to have them go ahead and let us know or give us their feedback, thoughts, comments. I don't know if, Mike, you want to start
Yeah,
first or
I'd
Shane?
be happy to, or unless you want to.
Go ahead.
Okay, yeah, well, I really appreciate what you guys have done. It obviously is a very complicated, and with all this kind of like, the multifaceted stuff you're trying to balance, in your calibration effort, it's obviously very complicated. And plus, it's a very large model. I was asking myself, is this the biggest groundwater model ever developed? I'm not sure, I know, Cliff Voss did like Northern Africa one time or something like that. But it's quite large, I'd say, so it's quite remarkable. And it's gonna be difficult to calibrate for all those reasons, and and I think you're addressing exactly the right questions, like, are we gonna be able to, by looking at this deltas, are we gonna be able to use it for its purpose? That's really what's most important here. And I guess personally, I find it like a little disappointing that when you zoom in on some area, something doesn't work too well. And I'm sure you guys have been struggling with the same feelings. But it's just not possible to make that happen on a large scale, to have some kind of great calibration everywhere. So I think it's admirable what you've done. I have some kind of specific questions that I didn't ask when we went along, and maybe we'll back up to some of those and go through some of those slides again, like maybe, and I don't know who was responsible for some of them, but like slide 14, it was about the boundary conditions and stuff, and it was about the layers 2 through 5, I guess. And I guess what I was just gonna ask, does that mean that it's closed? The model is essentially like a no-flow boundary at that level, in layers 2
Oh,
through
in the,
5?
it's for the constant heads?
Yeah,
No, so what happens is because that edge that's no longer a constant head, it's just an active cell. So our assumption is that we have a constant head there in layer 1.
yes,
That represents the tidal condition.
yes.
So that would just perpetuate through the layers as an active cell.
And then that's the edge of the active cells, though, so right on the.
On the
other
edge of
side
that
of
is
it.
no flow. Yeah,
When it's no
it's
flow.
inactive.
Okay, that's what I thought, and it seems pretty reasonable, because we would expect all the water to be, fresh water to be coming up anyway. But yeah, I guess, I would be interested, if it's not too out of your scope at this point, to see some cross sections of what the chemistry looks like there too, how that's actually working. And it was actually interesting too, because then you were talking about putting constant concentration boundaries, I think, into the intercoastal, basically, in Biscayne Bay and so forth, right?
Actually, those aren't constant concentrations in
Okay.
intercoastal. They rely on the initial concentrations as the starting point.
Okay,
With the rivers, though, one of the things we simulated was that the transport from the river cells themselves did not adversely affect or change it wasn't providing transport from the river into the aquifer system. It assumed the same water quality at this point. Looked into trying to get that river package and reservoir package to do a better job of that future modeling types of things, but right now it tends to try to over freshen if you would have just left it alone.
Yeah.
Typically, the way that river package worked before, it would assume zero or freshwater completely.
Yeah.
Being used as transported to the aquifer system, so that wasn't very helpful.
right, yeah.
But it's what he was talking about, though, is in the river cells themselves, the initial water quality, we said at 18, for instance, within the intercoastal, simulating it as a river. So granted, we have, well, it is open water there, so the conductance is going to be higher and stuff like that. So the coastal constant concentration from the tidal cells, right, is providing a 36 with 36,000
Yeah.
TDS. So as that water comes in or fresh water pushes out, moving forward and back, we're letting the physics of the model sit here and support what's going on with the transport and the water quality.
Yeah. Well, I think it might be helpful to have a little more explanation of that. And I know the report isn't even finished yet.
Right.
So I think it would be, for me anyway, be help a little bit to understand how that's working there. Right, let's see. Oh, so I know I already asked you about the title thing, which did look like. Can we go to slide 23 and just check if that's the one I'm really talking about? Yeah. They just look like monthly averages to me.
There are some other title ones that
Yeah, that
Probably
have more
look like that.
fluctuation.
Yeah.
This
sure.
is just an example for Virginia Key.
Yeah. And it, it shows like our king tide season basically
Mhm.
every year. So it's quite interesting in that regard. And the trend is so strong. It's kind of remarkable. Okay, good. So on slide 25, I noticed that the classes that were presented, I don't know who's in control right now. Here we go.
Alicia, yeah.
Yeah, so in the draft report, I think it goes up, it's greater than 75,000.
Yes.
So it's different, for whatever that's worth to you guys. I mean,
I think that may depend on which, so in the draft report, chapters 1 through 4, what was presented for the the KH is from the APTs, what was Crete. And this is what's actually in the model.
I see.
So there's a difference
Okay,
there.
okay. Well, I guess the report will have both.
Yes.
Okay.
So we have in the, I think it's a part of an appendix or something where we put all these maps in there.
Okay, sounds good. And let's see, slide
Can I-
27, go ahead. Yeah.
So, we have 5 layers. And as you know, with APTs that are done at any location, it's related back to the casing depth and open hole interval of every well.
Yeah.
So as you can imagine, any of the historical APT data that we have, none of them match up exactly with the 5 layers that we've developed. So the values that we get from the APT are, from that specific, tested interval, but then we have to translate that into the 5 layers that we have. So it's a challenge to present that. It may look, when you present the data, it may look like we haven't captured the full value of the APT, when in fact it's because we're looking at, 1 or 2 layers as opposed to the tested interval. So it's a challenge that we recognize and we struggle with a little bit, but that could be another reason why displaying it looks a little bit different.
may not cut all the symbology ranges too. It's like, it just says greater than 50,000. They could,
Yeah.
there could be a higher one. I don't remember what the max
Yeah.
value is.
Actually, I mentioned it verbally, the maximum observed is.
It's 75,000.
Yeah.
Yeah. In layer 3.
Let's see. Oh, slide 27. Yeah, so I guess one thing I noticed going through and I'm sorry, I already forgot the name of the system where you look at stuff, but
Oh, stats. So
I have a couple of graphs here that I pulled out yesterday, and the bottom line, I think you showed some of this too, and you probably have some, but my perception for a bunch of the wells I looked at was that the peaks weren't being captured from big rainfall events, and the bands of the simulations were a lot narrower than the actual fluctuations. And so, this is the parameter I look to kind of explain that. And, for many of your purposes with this model, that doesn't matter that much. But for, I think you might have mentioned somewhere in the report about flood tying in with flooding. I think for that purpose, it might be a lot more important. So this seems kind of high to me because of the 0.2 value seems high, because if it was lower, you'd get a bigger response to those rainfall events. And further, I didn't notice this on your list of calibration parameters. You mentioned storativity, but you didn't have this on there. So I was kind of curious about that too. Why it wasn't.
The specific yield.
Yeah.
It probably should have been, because that's why we have localized changes.
Yes.
So when he says it's 0.2 with localized values at 0.1,
Yeah.
it's from the sensitivity runs, and then
Okay.
we said, okay, it responds better to 0.1 in this area, so we reduced it, yeah.
And regarding the dynamic responses, yes, absolutely right, especially layer 2 through 5. So that peak and trough data, actually, when we took this value, about 100 wells went into a better R-squared value.
Mm.
So yes, it shows a very good dynamic response, and that's why we chose that value. So
Okay. Let's see. Oh, can we go to 35?
35?
Yes. And I think these look great. I've kind of wrote in my notes, it looks really nice. But the interesting thing to me is that they're all in the same units, and hence, they're, you know, at least for comparison's sake, there might be some value to being able to, you know, compare them directly, because if you just look at one and say, well, there's so much of this and so much of that. And then, you know, one thing that struck me, having worked on septics in Miami-Dade, in terms of recharge, some places they're saying it's like 20 inches of recharge, which I don't see popping up on here.
Kept in return flow.
Yeah, yeah.
So it's the orange is the 20 to 30, and then the brownish color is less than 20.
So maybe it was kind of captured to some degree, but yeah, it could be. I was just astounded when I learned that that was the estimate. Really interesting.
yeah,
Septic.
I noticed they use septics for runoff, right? You just to remove the runoff from certain areas, and then they are.
Yeah, but septic, 20 inches of septic recharge.
Yeah, you find it in that Hughes and White urban Miami-Dade model report, basically.
Was that a measured value or a result of calibration?
It was not calibration,
No.
it was from some like population and discharge estimates based on.
That sounds high.
Yeah,
I thought, you know, I thought it was amazing too.
yeah.
But it's a lot of people.
And if you look like the domestic self-supply wells out there,
Shocking.
everybody's like, but you've got WASA, and I'm like, yeah, but I mean, I got you know, working with Angela and Martina, they got me a coverage of spatially each house that doesn't have sewer, doesn't have, you know, and I'm just like, this is astounding.
It is.
Yeah, it's crazy, but yeah. Okay.
All right. Yeah, so slide 58 is just the one about calibration that didn't mention specifically.
Mhm.
And then I also had a question, and I think you explained it to some degree, and this is the thing I was just asking about, you know, when you wrote boundary condition conceptualization on slide 60. In the, you know, and I didn't quite understand what that meant there, but you guys sort of have explained it to some degree. But I think it's really important because, again, looking at the data platform, it's amazing. Some places like near the coast, the salinity is actually going down. What, you know, the real data are going up, but it's a little hard for me to understand why that would be the case, I guess. So the boundary conditions, I think, as usual in groundwater models, are really important, and, you know, may deserve some attention.
Yeah, and that's something that we kind of I actually, you know, thought about, and what I've seen is a lot of people use SSMs to represent river cells.
Yeah.
Because that could be a source of, you know, higher salinity coming in that we did not do in the model.
Yeah.
So that was, we thought about it, and I think we tried putting SSMs in, but then we almost felt like we were like cheating.
Mhm.
You know, because I'm specifying what the concentration should be. So we moved away from that method, but then I think the result of that is I have this somewhat freshening towards the coast, which we know is also not, you know,
Right,
so it was a counterbalance of.
yeah. Yeah, it kind of gets back to the whole scale of the model versus where some of these really big pumping centers are in dense urban areas, you know, like kind of be wondering, it probably would not be best to use this big model for those particular spots, you know, this is more refined.
Localized project
Yeah,
or something, yeah.
exactly, yeah. So just the way it will have to work out in the future, yeah. All right, so let's see. I have some other really tiny things that I will probably just share with Alicia, I guess, and see, you know, more language things and so forth. But I'm looking at a couple of these, I don't even know if I can read the, you know, examples of the situation I'm talking about where the salts are going down. But maybe it's bigger, maybe I can tell you which ones. Maybe we can pull up that system for a second too.
Are you looking at some graphs that you downloaded
Yes,
yesterday?
yes, exactly. So like F-279, for example, it's in North Miami.
Do you know how to navigate to that?
No.
You?
And you know, it just makes the point I just said, basically, so it doesn't, it's not really critical. Something that just will do.
Yeah.
Well, this is the time to,
Yeah,
you can address it now.
yeah.
No, but it's loaded on that server. Yeah. It's a water quality graph, right?
Yeah, that's right, yeah. Right near North Miami. Oh, you have a different way of
Oh,
accessing.
yeah, and I
these
think he's
things.
looking at the stats, you think?
Yeah, yeah.
But she's got the actual.
It's hard to see off a stats view because it's so small. I
Oh,
can
okay.
just pull up the
Which one?
F-279.
Yes,
F-279?
So you just find F, go all the way down. It's in alphabetical order.
You write some search for it.
Sometimes that doesn't work for some reason. I don't know why. Oh, there you go.
so this is an example. You know, if it's where you need a well, it could be kind of devastating.
Right.
Yeah.
Yeah, with this S view thing, it's like it might actually help you see what's
Yeah.
surrounding it.
And then maybe we could just pull one example up of the water levels too, and I'll give you one here. You know, I was looking at ones that were, I was biased, I was picking the ones that were bad. You know? Well, because, and the ones.
You're
there-
a glasses half empty kind of guy.
How about the G3562?
And that's water levels or water
Yeah,
quality?
that's water levels.
So Lisa, you gotta go to the water levels folder.
It's just a, yeah.
Level hydrographs. G, which one?
3562.
It goes, scroll down and then it goes to the thousands. Go up a little bit more.
Yeah, it's good. Doing good.
So, yeah. And obviously, there's a lot more peakedness in the.
Yeah,
items. Maybe there's just one other thing I'll mention, mostly the text, and it was in section 3.2.2. If that's easy to pull up, Alicia, I don't know.
The document,
Yeah,
chapter 3.2.2. Sure.
you have to guess if it's an A, B, or C.
No, well,
You have it together.
so after meeting and figuring out how to like, that was it, splitting it up into like 5 pieces was just brutal. So now what we're gonna do is we're gonna use that secure FTP site.
Okay.
And that way we can keep everything together instead of breaking it up into multiple pieces.
Yeah.
Were you both able to access the FTP site okay?
Yeah, I did. I tried, but it wouldn't seem to work for me.
Okay,
But the other, I was able to get all the data through the other.
Okay.
sites.
And then docs.
No, it's not in here. Where do you have chapters 1 through 4 initiated?
you're the one that,
I think that one I may need to.
you
It's on the
created a
web,
PDF of it.
Yeah,
In the web board, it's like several pieces.
yeah.
oh, but not,
Well, no, on the web board, I did post 1 through 4.
yeah, but it was chapter 3, how many pieces was chapter 3 broken into?
Well,
And
series A, C, B, C, D.
I don't remember because it's not my desktop. We have it one of this. Which chapter is it again, much?
Chapter 3.2.2.
Yeah, 3.2.2.
It's not A,
Yeah.
by me.
Might be down as far as. And it's just about the hydrostratigraphy
Okay.
indeed, yeah, so somewhere here, it's 3.2.2.
2.2.2?
Let's see if we can find that.
There we go.
It says hydraulic day, let's see. Though I have the words written here. A thick clay layer, or right there at the top, due to the presence of a thick clay layer. And I guess I don't think of it like that, in terms of details, right? I mean, we're talking about the hawthorn and
Yeah.
stuff, right? But
Yeah.
I mean, it's isn't it more limestones and maybe lower permeability materials, but I think it's.
There's a lot of clay to it, but admittedly, there's others, there are silts and limestones and stones in there too.
It's just not
Okay.
what I'm used to, how I'm
Yeah.
used to hearing it. And thinking of it personally.
Fair point, we can fix that.
Also think the figure 3 tool should be 3.4.
Ah.
Yeah, I mean on that page, you need to go back to that page. There's a
And then
label figure 3.2 and yeah, so I thought it should be 3.4.
You thought that should be figure 3.4?
You can
can
put
check.
these things in our written report
That's-
too,
yeah.
obviously, right? Yeah.
Right.
I guess the last thing I might bring up is,
Maybe we call it 3.2 real quick, Lisa?
The figure?
Yeah.
Sure.
You're saying it should be 3.4?
You have to go up.
Let's.
I think the figures.
Oh, yeah, that's right.
Yeah, that's right.
Yeah. Okay.
yeah, so the last thing was interesting to me, and it's the treatment of the Everglades agricultural area is kind of different, where the surface water and the groundwater almost seemed like they were being disconnected there in the sense of like you weren't, when there were demands for water, it was all coming from surface water, but it wasn't like impacting groundwater or something. Maybe I just don't really fully understand how that was handled, but I got a sense from whoever was speaking that it was being treated differently than anywhere else.
I think, it's simulated with the river package, right?
So the difference in the EAA and everything else is that it's simulated with the river package. Typically, and even in previous models, when we had the EAA, we usually just put drains everywhere. But we know that the EAA is a little bit different because it's managed,
Yeah.
right? So that's why we chose this time around to model it with the river package. Now, typically in our groundwater models, we don't include surface water demands.
Yeah.
So anybody who's pulling water from the surface water system,
Yeah.
regardless of where they are, we don't include those demands.
Yeah.
But really that's it. That's the only difference there in the EAA.
Because I'm just trying to like understand what that means, like not to include that demand for one of the biggest ag areas in South Florida.
Yeah, so I guess typically what we say is, and it's not just the EAA, anybody who's using surface water
Yeah.
across the board.
Yeah.
If they even have any type of surface water, we just exclude that demand. So our system of belief is that if you have surface water as one of your sources, that's what you're relying on. You would only use groundwater if for some reason you're cut off from the surface water feature. So we don't include any of that pumpage. So even the areas to the north that are bordering the C-44 canal heavily rely on surface water. We're not including those demands. So that's just kind of our like a governing principle of our groundwater models, that we don't include those surface water demands.
Nushi, can you talk about when we get to the application phase and boundary conditions coming from 2x2, how that
Sure.
could be?
So once we are moving into the application of the model, essentially what's going to happen is for our constant head data set, let's say, everything along the tidal boundary is going to come from a tidal data set that our regional model, like our surface water modeling crew or bureau, they handle that. So they're going to send us all those tidal conditions. They're also, so we have a slew of surface water models in the district. Previously, we used to use the water management model, which is a 2x2. That one doesn't have all the new product features and CERP components built into it. So what we're using for ECSM is a combination effort of the RSM GL, which is used, you know, in that southern Miami-Dade region.
Mhm.
We are getting all of our river stages from them. So they're going to be providing every canal, you know, in the rivers package. All of those state daily stages are coming from them. When you move north or into south of C-51, but north of the GL boundary, we have the RSM-BN, which is a bucket system essentially. And what they have is they have flow and not stage, right? They have one, but they don't have the other. I can't remember which
Yeah.
one it is. So what we did was we then developed relationships based on historical information to say over time, historically, if the flow through the system is this, then the stage is this. And we developed this time series of equations. And so that when they provide us, whether it's flow or stage, we can then use that series of equations to get the counterpart that we're missing for the river package. So all of our boundary conditions as we move into the application is going to change to match their data. And the reason we do that is because, especially not necessarily the planning runs, but our data sets, like our climate, for example, that's why we rely on the district data set. That's the data set they use.
Yeah.
They're going to be responsible for developing the rainfall scenarios, the drought scenarios, and things like that. So we wanted to make sure we were lockstep with them in getting everything in there. So that's kind of, it's like a joint effort in the application side of things for us.
Yeah, I guess where I was going is that those boundary conditions that we're getting from RSM and such, those have the surface water demands baked into it.
Yes.
So that's how we.
So their canal stages will take into account the surface water demands.
I mean, do they come from the groundwater ultimately from the canals? Like, I mean, if I,
Yeah.
Not all of them.
Yeah.
well, but I mean, but if I put a pump in a canal
Mhm.
and I use it to irrigate my field, Is
Yeah.
groundwater gonna flow in there?
Yes, yes.
Yeah.
And so I think,
You just hit on the limitation of groundwater models as opposed to integrated groundwater surface.
Yeah.
concepts,
like, I'm like,
Which would be another level of complexity above and beyond what we already have.
but I think the RSM, at least the GL, has like a layer 4 groundwater. So they do incorporate, they won't stratify it into like 5 layers like we do.
Right.
But they are including all of our groundwater demands are also included in their model as well.
All right, thanks.
Thank you.
Yeah, I think I agree with most of the overall impression about this model and the model motif. I think the model is large, very long time, the calibration period and the verification period. And with the complexity of the surface, the integrated surface and groundwater interactions, part of wetland and the soil diffusion and you guys really do a great job of overall, like looking at the calibration results. Of course, sometimes it's close but not reach the goal. But I think it's not one shot. Modeling always like a calibration, like a iterative process. You have to change and upgrade the model on the way going. Another thing is, I think you mentioned that you look at the use of model. I think that's more important rather than just because it's such a huge model. Yeah, probably look at the difference. In my career, I use a lot this method, but just calculate difference. Because there are so many uncertainty, so much uncertainty associated with the model. So I just do one with our project, with project, subtract them.
Yep.
To see the net difference between them, and you get at least much better understanding. Otherwise, there's so much noise in the results, right? So also you just mentioned probably use a local model. When you work on some smaller project, and so just use a local model, you can look into the detail in the final grades to see how the well boundary associated with the water quality change. I mean, like you here 1,000 feet, probably you could have several wells in the same cell, right? You lump them together in the center of the cell. I think that's another saying probably in the future into a regional model is only provide a framework, boundary condition, initial condition that you can work on the small scale and a localized problem. So I think that's overall. I think the model is it's complex enough, and the model calibration has been pretty well, and to reach the goal, at least with a focus on the application of the model for the future. So of course, and hopefully some details when more data come in, and more calibration will be done, and so then, as you said, the verification period, because more data, the verification period is doing better than the calibration, right? So that's and when we move on, we get more and more data. So yeah, so yeah. So that's overall. I think I really, after 3 years, working with your team, we learn a lot, and your thought process, you have a great modeling team. Yeah, you have our integrated, the great smart man together, really working well. Yeah, as myself, I know a lot from you and during the process, and so. Okay, so then, just before we run out, maybe I can we can put a question into our report, right? So here, maybe just one general question. When you convert, you mentioned convert the water quality data from different sources, it could be the chloride data. So what equation you use, how you convert them, because that can be complex.
It's very complex.
So
the process that was used, we have a water quality bureau here at the district. And so I went to them and I got from them a data set that covers a full range of data. So it has chlorides, it had specific connectivity, and it had TDS, all observed data. And the range of that data is from the fresh, like, I think 10 or 20 milligram per liter in a chloride, all the way to the hypersaline FPNL data. So we wanted to make sure it would cover every kind of data point that I might possibly see. And then what we did was we said, okay, let's develop relationships for every section of this data. That's how we came up with this binned approach, right? So, and I can't remember right off the top of my head, but if I remember correctly, if your chloride value was between 0 and 250 maybe, I had one trend line to convert everything over. If my chloride was from 250 to something else, I had another equation. And we just kind of created these bins for chloride data. We also said, and I can't remember off the top of my head, there was one where it was just like the 0.8 to the, take the chloride, multiply by 0.8 and you get the TDS. That was for like the closer to the seawater condition, right?
Above 8,000.
Was it above 8,000?
Yeah.
I'm glad they remember. They scripted it out for me because we weren't gonna do this manually. And so that took care of the chloride to TDS conversion. But what I also noticed is that our error was reduced if we went from chloride to specific conductance first and then to TDS. So that's not what we ended up doing. Is I think 0 to 250, I just went straight chloride to TDS. Then anything greater than 250, anything greater of a chloride of 250 to 8,000, we went from chloride to specific connectivity, then to TDS. And the specific connectivity was, I think, like 10 bins to get from, yeah, so it is a very complicated system. But we took it, we looked at, I had one set of data that I had observed for chlorides, specific conductance and TDS. Then I had another set of data that had all three, but that I checked for error. So that's how I determined when my equation is good enough. I just did like a verification. And then made sure that the Water Quality Bureau also bought in and said, okay, yes, this makes sense. You're not totally off base here. So but it introduces a lot of error, right?
Yes.
So that's,
So is that going to be covered in the report?
that will be covered
Yes.
in the report, yeah.
Okay, so right now, so as a panel, so we are going to review this thing. So I have this short version of the report, right?
Yes,
So, we are expecting a longer version or?
yes. So that's in our next
Next slide.
steps, I think, yeah. So we have a next steps slide
Yeah.
that's gonna go over kind of what we're seeing as the schedule for moving forward.
Okay, so this review only focus on the calibration.
Yes, so what we did was we put together, like the conceptualization is basically what chapters 1 through 4 are. Then we wanted to present the actual results of our calibration. Then we're gonna write up the next draft chapters, which is basically all the model input, the conversions, everything that we've done, the model calibration, and then get that to you. And that'll be the full, between 1 through 4 and the new chapters, that'll be the full documentation.
Okay, what time is we expect to get that?
I think we said December.
December.
Yeah.
Oh, that's-
Well, before we get to the schedule, do you have anything else you want to address on your comments, at least from what you've seen today and even on the first 4 chapters that you do there?
Yeah, I think that's I said there was many questions and let's skip that and we can present the report into one we review.
Okay, okay, so
So
your questions are more about, making potential changes to the wording of the report, not the big picture. Is that what you're saying?
No, I mean, my question, as for question, it's not that manner. Some are like, for example, the 1 to 10, the vertical hydraulic conductivity, how that came out to that final calibration results.
Okay,
Did not talk about it here, and so just assume 10 to 1. A lot of people say that's not 10 to 1. I just want to see how that impacts
Sure.
your calibration.
Yeah.
So
okay.
yeah, that's kind of it's almost lunch time. So I just want before we finish, and at least we get the scope of the review. So So how do we handle this review? What time to get done and so, okay, so right now we can put together.
Yeah, definitely. But you know, you're just making me think about something here. So you're gonna try this pest calibration next, and I think there could be a lot more kind of sensitivity analysis.
Yeah, so the way that we have the issues that we're having with putting or running the global sensitivity with pest is the size of the model. Right, so right now our output, I think, is like 75 gigs for the heads and 75 gigs for the TDS. And then it's 32 gigs for the cell by cell. So in order to do the thousands of simulations that we need for the global sensitivity, we're not gonna have enough space. So what we're trying to do is kind of clip out like, let's focus on this year. Let's focus on that, like pick a set of years that we want to calibrate to. And I'm kind of almost leaning towards picking the current years because we know our data is better. Going with that, and then we're gonna provide the list of parameters that we want us to look at. And essentially, what's typically happened is we'll run pest and it'll come back and say, okay, here's where you could have made changes to get a better calibration and things like that. And then we would write all of that up in the report.
One thing that did, Walter got with me, wanted me to check into whether we could change up the output to have, HOB and the TOBS packages instead of exporting the EDS and TDS.
Yeah.
So like I said, I definitely look into that.
Yeah, just
Sounds great.
some kind of way for us to have, because 75 gigs is just too, it's too
Yeah,
big,
seriously.
so if we can find some other way to not have to export that file size and then have an observation package, then we'll try to do that.
I think you're talking about like a subsampling of the.
Well, yeah, rather than every single
Yeah.
cell, right? Even with the observations, it's like, there's what, 800 wells or something for.
Yeah, we have like 666 wells, so that's still,
And those won't be binary, those will be ASCII, so.
So how long it takes to run the whole model now?
we're about 20 hours.
So what do you expect to run the model with the pest?
Well, if I can cut the simulation period, we might be able to get a small runtime. I know when I focused on just Miami-Dade, my runtime was only a couple hours. Wasn't too bad. So, we have a couple of options of what we can do. So we're gonna see kind of what we can come up with for the second part of it.
So with the past results, do we expect that will change the calculation? So far, we saw significantly.
We're hoping not. But we're gonna have to see what it says. We're really hoping that it's because we did all that sensitivity analysis to begin with. We're hoping that pest is not gonna give us something that we're, not expecting to see.
Yeah, because from now to December, only tomorrow, 3 months.
I know,
Yeah.
I know.
It's a lot of work.
It's a lot of work.
To do that.
Yeah.
Yeah, okay, yeah, we can work together to provide some more specific question, comments on that. Good. Yeah, general, yeah, pretty good. Yeah, so far. It's good, it's over.
All right, so if that concludes the discussion for now from the panel, we'll go ahead and move with go back into presentation over here. So we'll move forward with the public comment. So if you are participating via Zoom, you can use the raise hand feature. If you're participating via phone, you have to press *9 to raise your hand and *6 unmute your line. So when you are called upon, please state your full name and affiliation prior to providing your comments. Each person commenting will have 3 minutes in which to provide their comments. Sorry. So with that, I'll open it up for public comment. Okay, I see one raised hand, so I see Angela Montoya, with my name. Angela, you can go ahead and unmute.
Thank you, team, for the great presentation. And it's a tremendous amount of work. One thing, just that about the septic systems, when I converted that flow into inches per year in a specific cell, in a cell of 800 by 800 feet, I got a maximum of 10 inches per year. So I am not sure, like the 20 inches per year, like if Dr. Suko mentioned that, but the max that I got for the year was 10 inches per year in a high, well concentrated urban cell.
Yeah, that's substantially lower. And was shown in that early report, so.
Angela, you said the max was 10. How much is the average?
The average, I don't know. I just got what is the maximum that I have in a cell, and I got in per year 10 inches, but I don't know the average. I just went through because I wanted quickly to check
No,
the
no,
value.
Thank you.
Thank you.
Is that it, Angela?
Yeah, that's it. Thank you. Thank you.
Just give it a few more seconds here to see if I see anybody else raising their hand. So far, I don't see any additional hands raised. Going once. Going twice. All right. I guess we can close public comment. So, oops, we need to start the countdown again. Next steps. Anushi.
Okay. So as discussed, we kind of wanted to get your thoughts on the calibration, how we did, making sure that you, as our experts, that you agree that with our opinion that this model is good enough for its intended use, which is the water supply planning tool. And our goal is we've gotten you chapters 1 through 4. If you can get us feedback on those 4 chapters by next month in November. And then we will be posting the remaining chapters of the report by December 2025. And then if you could get us feedback within your calibration report by January 2026, that would give us a month to respond to those comments and questions. Or, sorry. Yes. Oh, no, sorry, I messed up. Okay. So we'll get you the draft calibration report in December. You would respond to the calibration report in January. And then get us the final peer review report in February. And then we will respond to the report in March.
Sounds good.
And of course, if I can get things out before then, that'd be great, but let's see.
We know the holidays are there, so.
Yeah.
So the report not including the application?
Not including the application.
Nothing related to application. The only thing, I mean, when we talk about application, I want to talk about this, just I want to reiterate some of the points that Anushi said, and it kind of especially came through when you were looking at that one F297, whatever it was, that the well didn't look good. But I think what Anushi was able to show, and obviously with StatsView and others, you can look a little bit deeper. I think on an individual well basis, there's going to be some wells that we didn't capture, but overall, but the way I'm looking at it is when we start applying this at a regional scale, when we apply a 20 years into the future and looking at the increased demands and looking at sea level rise and stuff, I'm assuming that at the conclusion of that difference between the 2045 and the base condition, there's going to be some areas that are showing some intrusion. And from my perspective, as long as the model can show that it's meeting its intended use. It may not show it at well F297, but if there's a well close by, like in Anushi's example that is green, that it can show the intrusion, I think that's the important thing from that bigger picture. So when we're doing the water supply plan for the Lower East Coast, we're looking at that macro view. And so for the 20 years in the future, if the model is capable of showing that there's saltwater intrusion that's happening, I'll just say Pompano Beach. Maybe as long as the model in the future can show that there's saltwater intrusion happening, it's not really as important on an individual well basis whether or not it shows it, as long as somewhere in that area it is showing that intrusion is happening in Pompano, for example, that's the intended purpose of a regional scale model. And I agree, at that point, it is up to maybe the city of Pompano Beach to say, hey, you know what, we need to look at a little bit more refined level because we want to see exactly where it's happening. Maybe they would alter pumpage from their northernmost portion of their eastern well field to try to address an issue. That's not really the purpose of what we're trying to do. We're trying to show that 20 years into the future with an assumed sea level rise, that there could be pockets of the Lower East Coast that might be problematic from a saltwater intrusion and sea level rise perspective. I think that's the purpose of what this regional model is supposed to do. And so from my perspective, I think I would like to, I think we're trying to emphasize to you all that we think the model is sufficiently calibrated to answer that regional question, but on a per well basis, we recognize that there are limitations for a lot of different reasons. Another, we talked about this at the previous meeting is on the water quality. There's variability between people that take the water quality samples. There's variability between the different laboratories. I mean, there's so much inherent variability just in the data before you even get to model world that we're having to deal with. And that's why, we can never get to 100% calibration because the data doesn't allow that. And so I think I'm looking for when you do your final report is that recognition that there are data limitations that preclude us from getting every well calibrated or within the error bands that we've selected. I'm looking for that sort of an acknowledgement that yes, you've achieved your goals, and it appears that the model is capable of simulating future demands and potential effects of sea level rise and saltwater intrusion on the groundwater system from that regional perspective. That's what I'm hoping that your final report will acknowledge that the model is meeting its intended use, but certainly not on a per well basis. But so also that even on a per well basis, there could be a well close by that is capable of simulating saltwater intrusion as demonstrated during the calibration process, and therefore the model can be used for its intended purpose. Now, if there were areas that we didn't have, I'll use red and green meaning calibrated and red meaning not calibrated. If there were areas where it was all red and there was no green whatsoever, then I think we would be the first to acknowledge that, hey, we may not be able to predict saltwater intrusion in the future in Homestead. I'll pick on, I'm not saying I'm just picking an example of an area that if there were a whole bunch of red wells that were not calibrated, then it would be, on us to say, hey, we're acknowledging that the model shouldn't be used in Homestead because we have all these red wells. I think that what we're able to display to you, though, is that although there are examples where we have red wells, close by, we have examples where there are green wells. And so therefore, we think the model is capable of meeting its intended purpose, but we want to get your opinion about that as well. And so I would like you to make sure that you cover that in the course of your review of everything that we've done. Because that, if there was concerns about that, we definitely, need to know about that. From our perspective, looking at all the data in areas where we have the red wells, we think close by there are some green wells that will still allow us to identify areas of concern from a saltwater intrusion perspective. So that's why we have stopped. We recognize that we could probably spend another year and maybe get from 70% to 72%. But we don't think at this point in the process, having turned all of our knobs between structure flow calibration, wetland calibration, making sure that the groundwater velocity vectors are pointing in the right direction, and the water level and water quality calibration, we feel that we're as good as it's going to get, and we could spend a whole lot of time and really not add a whole lot of value anymore. So that's why, Anushi mentioned we haven't seen you in a year. That's because we've been working, but we feel now that we're at a point where we think it is, it's time to stop, and we think we've met our goal. And so what we're looking for you, hopefully, is that after you review all this information, that you are in concurrence with us, that we think the model is good enough to apply it for its intended purposes for regional water supply planning analysis. So that I just wanted to emphasize, that's, again, the reason we stopped is because we think we've met our goal, and we could spend more time, but to what end? To get up from 70 to 72%, I don't think that's a very good use of our resources to try to do that. In fact, next year, we're going to be starting our Lower West Coast model and converting that from just groundwater only to density dependency. And we have learned a lot from the input that you provided, as well as our own rolling up our sleeves and going through a bunch of things, looking at what's the best package to simulate Lake Okeechobee? Is it the river package? Is it the reservoir package? We've learned so much that we're ready to apply in some of our other modeling areas as well. And so we're looking forward to doing that as well. But that's why, as a resource manager, I have to say, it's time to stop. We need to have this crew that's in this room right now. They need to start working on the Lower West Coast Surficial intermediate model to do this the same thing. In addition to, applying this East Coast model in the near term, we need to start working on our density dependent upgrade of our Lower West Coast Surficial intermediate model to be in the same position that we're at now. But again, we've learned so much from you all and the input that you've provided over the last 3 years, and hopefully over the next few more months. So we're looking forward to your report. But I just wanted to just lay that bigger picture out of that. That's why we've done this whole effort, and it's been a monumental lift from all of our staff here, and with input from you all. I know a lot of stuff about initial conditions. We had a lot of discussions about that, and we've learned a lot about how to we did it before, but I think we've really upped our game on how to do stuff like that. So I want to thank you both for that type of input, and so I just wanted to share that. That's where we're at. Does that make sense?
Yeah.
Okay.
Good.
It also brings something else to mind,
Sure.
which is from my other, less optimistic perspective, I guess. But it reminds me of like a machine learning situation where we have a sample, there's been the past, and we're going to fit a model to it. We've done that, calibrated it, but then we have interests in things that are not in the data sample. So that's something we might mention too, just in a sentence, because it's that's where the risks with these types of things lie. So some of your needs, I don't think we've checked to see like what the impact of additional sea level is, or what happens, how does it feed back into the levels in the intercoastal, so on and so forth. There's a lot of complications that come up there too. So
yeah. And we recognize that it's very possible that when we get into the application phase, that there are going to be some, when we go through a long calibration period and we go through a verification period, and we look at how the model's behaving, we make some alterations, but none of those things look exactly like the predictive simulations that we're going to do, a 20-year simulation, a 50-year simulation. We don't know how the model is going to respond to that, and it could point out some areas that we want to make some adjustments. I think that's part and parcel with modeling. So I think we're conceptually prepared to look at that, but we won't know that until we get to the application phase, which is the next part.
So
yeah, it may expose something that we did not capture in the calibration and verification phase, just because of the effect. I mean, we're not, you know, we haven't looked at raising sea level 1.5 feet and seeing what the model does. We don't know that until we run it. And so we're just as curious as you are about, you know, how the models can respond to something like that.
So with that, if there are no further comments, that concludes our presentation. For today, I want to once again thank Wishing and Mike, you know, for coming down here in person. Felt that, you know, it'll be better, you know, seeing you guys here in person and having you guys here to have this discussion. So thank you very much, you know, for participating on our panel. Thank you to all of our staff, tireless, countless hours that we put into, you know, getting to this, you know, stage that we're at here, you know, finalizing or making sure that we could calibrate it as best as possible. And then, of course, to folks participating online, thank you for your participation in today's meeting. And with that, I will adjourn this meeting.